Baji? Oh my goodness. Happy New Year to everybody. It has been a little while. We really missed everybody, but here we are. Here we are. We're live. And thank you so much for joining. Baji is ready to wish everybody Happy New Year, along with his siblings, Fuji. And we also have Suji over here. How is everybody doing? We're gonna be live and we're gonna wish everybody a happy new year, and we're gonna cover some physics topics as well, and we'll chat and catch up. Hi Ram Candy, how are you? Happy New Year! Oh, hi Doro Doro. Doro Doro says, dang, I got in early for once. What's up? Happy New Year. We're good. Here's Baji. First, like, thank you. Thank you, Ram Candy. Here is Baji. I'm going to sit us down over here. So here we are. Look at that. We have Baji. I have Fuji. I have Suji. And we have Ram Candy. Doro Doro, first like, thank you so much. Thank you, thank you, thank you. Let me share the live from my laptop real quick. Hi, Fuji Baba. Hi, Fuji Baba. We have been a little bit MIA. Sorry about that. I've been dealing with some family stuff, some family friend stuff. But here we are. We're live. Yay. Ram Candy, Doro Doro. Thank you for the emojis. Thank you, thank you. Let me see. Let's see how it be. Let's see if I can share the live and continue our chat, get together, catch up with everybody. How is everybody doing? So Doro Doro, what did you do for the New Year's Eve and New Year's, the first day of the year today? So today is the first day of the new year, so I am making sure that we spend it together. This channel hopefully will have lots of more growth, and we can learn a lot more together and everything like that. So thank you so much for being here. Thank you. Thank you for liking the live. Thank you for sharing the live. Thank you for being here. Simple party, says Ram Candy. I relaxed. I partied hard last week. Oh, really? For Christmas? Wow. Yeah, I also had a simple party. Like last night, a couple of my friends came and they came over and then they ordered pizza for me. So I like that style. I like when the friends get here and then they realize that I have no food, so they order the pizza. So Doro Doro says, I relaxed. I partied hard last week. Here's hoping the new year is good. Yes, me too. Catherine says, hola, Aviola. Hi, Catherine Nunez. Hi. Mitch says, cute. Hello, Mitch. Mateo says, hello. Hi. Hello, hello. As usual, I have forgotten to share the live because I get distracted talking to you guys. Thank you for being here. Welcome, welcome. Welcome to the live. And if you're seeing this as a video upload later on, welcome, welcome still. And thank you for being here. Yay. Okay. Shared the live. So yeah, yesterday, which was New Year's Eve, we just did a simple party. Just a few people. I got pizza, and on Christmas, we went out and I went out on Christmas Day. I got Malaysian food. Chinatown was open, so here in Boston, we got some food in Chinatown. That's where I recommend going if you're gonna be trying to get food on Christmas Day in Boston. So anyway, anybody else wanna chime in and say what you did for Christmas or New Year's? Happy to give you a shout out and chat with you for a little while. On this channel, we show the kitty cats. There's Baji. We also talk about physics. So today I'm going to resume my physics topic, but at first I want to just kind of catch up with everybody and hang out and make sure that everybody who wants to, you know, share something from their day or from the entire last year has a chance to do that right now. So, hello, welcome. Ooh, and also this sweater is a sweater that I have been wearing since I was a little child, and my grandmother made it. Yesterday night, small drink party. Nice. Yes, we also had a drink here, me and my friend. My other friend does not drink, so he just did a cheers without the drink. Mac tonight says, Mick, hello, I had McDonald's for New Year's. Good. McDonald's is good. Ram Candy says, me and my friends. Yes, very nice. Happy New Year, everybody. Happy New Year, Happy New Year, Happy New Year. Here is Baji, and he is ready to do some more hellos and highs with everybody here. And then, so remember, we were covering, as far as the topic goes for today, we had been covering some physics topics from various sources. We talked about, in the last year, we talked about astronomy, astrophysics, cosmology. We actually mentioned, we kind of went through all the different topics from the 20th century physics around the month of November. So if you're kind of chancing upon this live, I just wanted to say that we covered pretty much most of the 20th century physics topics, including quantum mechanics, relativity, including special theory of relativity, general theory of relativity, all of that, all of those developments, sort of in a popular sciencey kind of way in the live streams, mostly from the month of November. So we pretty much finished all of that, and we even saw some really entertaining stories of the debates between the various different scientists and physicists of that time, including the debate between Einstein and Niels Bohr, and really the foundational work that was done in quantum mechanics, especially in the 20th century. And by that I mean mainly in the first half of the 1900s, because really towards the later half, we have a much more sort of mature quantum mechanics and particle physics that are kind of, coming up and forming. Thank you. Thomas says, Happy New Year. I'm racist. Okay. Bram Candy says, you're so pretty. Thank you. So basically, we saw something like particle physics coming out of the developments in quantum mechanics towards the end of the 20th century, and sort of more in the beginning parts, even now, up to now, of the 21st century. So particle physics is really sort of a testament to the success of quantum mechanics and the fact that even though quantum mechanics was bizarre, a lot of people struggled with the concepts of quantum mechanics and the concepts of this sort of duality and the fact that sort of matter waves gave us the wave equation of matter, but really it was the probability it wasn't the probability of finding, or sorry, it wasn't the wave equation was not for the position of an electron, but the wave equation is for the probability of finding that electron somewhere. So this sort of probabilistic nature of the answers that we get from quantum mechanics, and the fact, of course, about sort of a duality in quantum mechanics, not just for something like light, which the fact that light, which is a photon as well as a wave, so it has both a particle as well as a wave nature. This sort of duality of light is considered the old quantum mechanics. So even someone who is maybe more classical, like Einstein, actually worked on the photoelectric effect and gave us the quantum nature of light way back in 1905. So he had a very successful, very productive year in the year 1905 and gave us something like the quantum nature of light. And we got the photoelectric effect just as a side hustle, because of course he's mainly known for relativity, the special theory of relativity, which gave us the relative nature of space-time and mass-energy equivalence. And then also he worked on general theory of relativity because he understood that special theory of relativity was sort of still for more special cases, inertial frames of reference, whereas there are, something a bit more general, which is the general theory of relativity, is more for where you might have accelerating frames of references as well. And so in the cases where you would have acceleration, then special theory of relativity doesn't work anymore. We would need a more general theory, which also explains gravitation. So those are the things. The special and general theory of relativity are really more what Einstein is known for, but he got the Nobel Prize actually for photoelectric effect. So this is just to kind of let you know that during the 1900s, early 1900s, in the 1905, 1906, like these types of timelines, 1910s, 1920s, these were very, very, very important years for the development of course, relativity as well as quantum mechanics. Even though Einstein is a godfather of this old quantum mechanics, which gave us the duality of light, turns out a number of other people worked on quantum mechanics and came up with even more sort of what they considered bizarre results, which gave us dual nature of matter as well. And we've talked about it in some previous live streams. De Broglie talked about matter waves, and he basically tried to almost like copy pasting the dual nature of photons and seeing, well, what if you kind of did that to matter, and what if you came up with like a wavelength or something for matter waves, right? And then Schrödinger gave us the more formal way of writing down the wave equation for matter, of course, where he wrote it down, and we've covered that in a few of our live streams. And then actually it was Dirac who turned those Schrödinger wave equations to relativistic Schrödinger wave equations. And then later on, I think it was I'm trying to make sure, I think it was Max Born, if I'm not mistaken. It's in a previous live stream where we've covered this, who realized it's not the position of an electron that we're getting from this wave equation, but the probability of finding that electron for the position of that electron. For example, for something like the wave equation for an electron within a hydrogen atom, for example. So something where quantum mechanics gives us the mechanics of the very small, and sort of what you get as you work on those types of things is something that works a little bit different than, for example, in classical physics. So these are things that we have covered in a lot of detail in the previous live streams, especially during the month of November of the last year. Now that we're in this new year, I'm kind of starting off with a big old summary of everything we've covered. And basically, now that we're in the 21st century, why it was important to lay the foundation of relativity as well as quantum mechanics, because not only historically is that's the history of science, that's the history of physics, that's how it all developed, but also right now the fields that are important and right now the things that are going on, it's important to understand the history of all this in order to understand where we are today. So right now, as we've seen, particle physics has come a long way, where in the past, maybe 100 years ago, where quantum mechanics was considered kind of weird, now particle physics has kind of come out, have been birthed out of quantum mechanics, and it's quite a successful field. It's still something that leaves one with questions sometimes, but along with that, there's a lot of evidence. There's a lot of evidence for real life things that are explained by particle physics, and more types of particles that have also been discovered by the field and by various people, many people who work on the various different experiments of particle physics. So, there might be things that are still considered a little bit bizarre. There might be things that are still considered to be a little bit like, oh my gosh, there are so many particles, like, what does this even mean? And does this really tie various concepts together? Because remember, one of the complaints in that 20th century type of development that people had, for example, the string theorists, what they complained about was that particle physics or quantum mechanics was adding certain questions that they were not being able to answer, especially when it came to the grand unification of all the different types of physics. Hi! Hello, Roman Arun. Hi. Steven Spears says, hi, Happy New Year, all. Happy New Year. Yes. Hello. And Dr. Seuss says, using classical physics. Hello. Okay, perfect. So basically, even though it's almost like quantum mechanics and particle physics kind of came a long way in the face of sort of some level of adversity because people were not, first of all, used to non-classical ways of doing physics. Classical mechanics or classical physics is very much something deterministic, where you get a deterministic sort of answer out for, say, the position as a function of time. This type of probabilistic nature of quantum mechanics was a big issue with a lot of people, and they did not really like that. But at the same time, quantum mechanics was describing reality and did stand the test of time as well as actual experimentation. And so it started to explain and give us evidence of real life things that were happening, including the hydrogen atom, way back in the last century. So people couldn't ignore it. And it has come a very long way. And we have the field of particle physics now that has matured a lot. Now, as far as the grand unification theory goes, which is to unify relativity and, electromagnetism and quantum mechanics and all these different major fields of physics, we still don't really have a grand unified theory. That question is still open, and string theory or superstring theory is supposed to be a good candidate for the grand unification theory. We've talked about that as well, but we also saw how there are some challenges faced by string theory itself, in that string theory cannot be tested because we can't really test a lot of dimensions, a lot of higher dimensions. There was this notion we kind of discussed as well, which is that, well, we kind of experience 4 dimensions, including time, the 3 spatial dimensions, and the 1 time dimension. But if you need a lot more dimensions than that for your theory to work, say 11 dimensions or something like that, even if you said, okay, like there are maybe these dimensions that we don't experience because they're very small or something like that, it's going to be hard because you might, if you can't test it out and show it experimentally, it's going to be very difficult because physics is an experimental science. I dedicate my new year. Okay. So that's sort of the big summary of what we've been covering, including relativity, quantum mechanics, how particle physics came out of all this. Electromagnetism, of course, we saw earlier. It's a more older, more mature field. We saw that special theory of relativity really illuminates a lot of the questions we had coming from electromagnetism. So we kind of talked about all of this. And we also talked about how the biggest open questions of physics at this time. So now that we've kind of covered the history, especially in the 20th century, we covered how really right now, standing today, the biggest questions are really what is dark energy and what is dark matter. There's a third question that I've also mentioned, which has to do with the origin of elements. We understand how most elements are made in stars. There are a few elements that are the heavier elements, but not the super heavy, sort of under barium atomic number, which are actually, there are still certain pending questions about how exactly, in what processes they're made. So to some extent, the origin of elements is still a third open question. I plan to buy a car this month and maybe move this year too. Oh, wow. Well, congrats, Stephen. So those are the open questions of today. Even today, right now, even after doing all of this work, we still have the open question of what is dark energy, which has to do with the expansion of the universe. What is dark matter, which has to do with all this invisible mass or missing mass that we found evidence of in our own galaxy as well as the universe. And it seems like it plays a big role in the evolution of the universe. And we've also tackled how these topics are kind of different depending on the approach you take. You can take an astrophysics approach, you can take an astronomy approach, or you can take a cosmology approach. So we also have covered a ton of cosmology actually in the month of December. I think more towards sort of the end of November and throughout December, the topics that we were mainly covering were more cosmology and including dark energy, dark matter. So remember, dark matter is a topic that you can kind of approach it from astronomy or astrophysics points of view, or you can look at it as a cosmology type of thing. We looked at the ingredients of the universe. Remember, there were 5, and these were quiz question. Who remembers the ingredients of the universe? What are the 5 main ingredients of the universe? I think Dora Dora was in the live when we talked about that. So this is a quiz question from the last year. Can anyone say anything about that? Am I lagging? Can everybody hear me? Okay. Nicholas, hi. I don't remember this. Okay, that's okay. So we talked about the 5 main ingredients are baryons. So that's all of the ordinary matter. Neutrinos, which was also important in the early universe, and the neutrinos kind of detached from the photon, electron, positron soup at one point in the early universe. Dark energy, dark matter, and photons. So I think those were, let me see, where is my, yes, here it is. So here it is. So if you missed my cosmology live where we talked about the 5 different ingredients, that's a shame. You might want to go back and catch that later on. So it's okay for now. We won't need this today, but it was actually a very interesting live. So if you go back to where we covered cosmology, you may find this that we talked about. So I think I might have called it either cosmology or 5 different ingredients of the universe, something like that. So if you missed it after this live, you may want to go back and cover it. I'm trying to find if there was a, yes, oh, that's right. So we called it, we might have called the live Cosmic Inventory. I love what the James Webb Space Telescope is finding out in the universe. Oh, good. Yeah. Maybe I was there. I do remember you having an entire live stream dedicated to cosmology. I had a few, so it wasn't just one cosmology live stream. I had a few cosmology live streams. So in at least a few of them, we covered cosmic inventory. So something like this might be the live stream title. So again, cosmic inventory is photons, which is of course light. The early universe was very much radiation dominated. Photons were what I call king of the jungle back then. They would just hit everything and everyone. So you couldn't, form neutral atoms. You couldn't calm down. You couldn't cool down. So photons are a big one. And then baryons, which includes, of course, electrons, positrons, baryons typically include only protons and neutrons, but at one point for the math of everything in the universe, we clubbed together baryons with electrons. But anyway, baryons are more about, ordinary matter. And then we said that there was a ton of non-baryonic dark matter. So that's the 3rd ingredient. Then we talked about neutrinos and whether neutrinos can explain, whether neutrinos can explain the presence of dark matter. And we saw that, well, even though neutrinos are very elusive, just like dark matter in that sense, but they're too low mass and probably don't account for dark matter. And then lastly, of course, we talked about dark energy. So those are the 5 things. So now you're kind of caught up. How does it feel to be a minority in the United States during these confusing times? Well, I don't like the bad ones. Okay, all right. How does it feel? I mean, feels like it always did, I guess. Came here to succeed, and here we are. So once again, the 5 different ingredients of the universe, or what I might have called cosmic inventory, and even this book that we have referenced in the past, it's called Modern Cosmology by Scott Dodelson. The 5 different things are photons, baryons, neutrinos, dark matter, and dark energy. So those are the 5 things, okay? So that's what we have covered in detail in past live streams. And for the sake of the math counting of how much of each thing one might one might expect to see, we kind of club together electrons in that same category as baryons, but technically speaking, electrons are not baryons. Okay, just keep that in mind. Baryons are more, strictly speaking, baryons are just protons and neutrons, part of the ordinary matter. And then really all of ordinary matter, if you club it all together, protons, protons, neutrons, cosmologists just like to call them baryons, plus electrons, positrons, those would all be sort of in the mix of things with ordinary matter. We're talking physics, not social and political issues. Yay! I have no problems with minorities. I'm a white man, but I do look at a person's skin color or the language they speak. Okay, so once again, this was a very interesting live stream. If you're interested later on, you can go back and look at it again. Photons, baryons, dark matter, neutrinos, and dark energy is what we talked about as far as the cosmic inventory. So remember that cosmology, there's sort of subtle differences between cosmology and astrophysics and astronomy. Astrophysics, astronomy, those are a little bit more specific in the sense of, okay, the questions that are about, say, our solar system, planets, our galactic center, sources of radio waves, black holes, trying to find life in other planets, trying to find stars that are sort of like our sun in hopes that we might find planets around them that are sort of like our planet. Those things are astronomy, okay? And then if you're trying to probe, say, a particular astrophysical event or phenomena, trying to understand why does this event accelerate these certain particles in this way, and why do I get gamma rays out of it? That's more of an astrophysics type of thing. And then cosmology is the study of the universe. It's not just about a certain single site of astrophysical phenomena or a single star or a bunch of stars or even a galaxy or even a supernova. These are all wonderful things, but that's not really cosmology. Cosmology is overall bigger picture study of the universe. How did the universe start? How did the universe evolve? The Big Bang nucleosynthesis, expansion of the universe, the fact that the universe is expanding and not just expanding, the expansion is accelerating, the fact that there's dark energy, the fact that there's large scale structure, the galaxies in the universe are not distributed randomly. There is a method to that madness, and we want to understand why the universe's matter density is the way it is, the galaxy distribution is the way it is. That sort of larger scale structure. And also that includes dark matter, the role that dark matter might play in the evolution of the universe. That is cosmology. Grimace. Hi, Grimace. Hello. Yay. Just admit you're looking to start trouble, probably because you don't understand the lesson she wants to give. Oh, thank you. So thank you for your support. But I wanted to real quick cover what are the differences. So cosmology is about the large scale, sort of these questions that we have about the universe itself. Not so much about our galaxy, neighboring galaxies. Well, if you're looking at, we did use redshift data of very far away galaxies to prove that dark energy is a thing, that the universe is expanding, so it's almost like you do astrophysics as part of cosmology, and maybe a little bit of cosmology as part of astrophysics. But when for it to be cosmology, it's probably going to have a much larger scale than in astrophysics. So we must keep all of this in mind. Depending on where your interest is, it might be it might be more under cosmology versus under astrophysics versus astronomy. Next is, I don't know much about, oh nice, I like to, hi Thomas, hi Grimace, hi Nicholas, I like you making this about race. Oh, like a race car? Race war, oh. I saw that and I was like, race car, vroom car. I don't know much about cosmology, but I like learning new stuff all the time, even at my age 59. No one made it about race until you brought it up there, Thomas. Who's Thomas? Oh, Thomas. Okay. Anyway, thank you everybody for being here once more. Welcome to the live. We are going to be covering physics and all this stuff that we've been kind of talking about. I wanted to give you all a summary of what we've covered already so that you can it kind of orients you to what we have talked about in the past, because I understand it might seem like you're in the middle of something when you first join. This chat is always crazy. There's not too many people right now in the live. Unfortunately, it can be even more interesting sometimes in the chat, for sure. So, cosmology, we actually, so Stephen, if you missed some of my cosmology lives, we actually talked about Einstein equations, the Einstein tensor, a little bit of general relativity math, the Ricci tensor, Ricci curvature, all of that sort of stuff, like sort of the basic math that you need, the metric, that sort of stuff. Basically, for cosmology, a little bit of that general relativity math is very important, and we did actually set that up in a previous live stream. I think I called it Einstein's equations, something like that. So, in the month of December, a lot of the live streams actually had the cosmology discussions. I saw you at the clan rally. Good to see you again. Oh, wow. Great. So now we will come to today's topic. So I have been referencing a bunch of textbooks and things like that when covering these topics with you guys. But when it comes to particle astrophysics, that's actually my own topic. I've been referencing my thesis for that part. So a few live streams ago, it might have been quite a few live streams ago, we started to talk about particle astrophysics. So now, what is particle astrophysics? I talked about the differences between astrophysics, astronomy, and cosmology. Those are all kind of different things. But then what is particle astrophysics? And I also talked about all of that summary about the 20th century quantum mechanics business, also because particle physics is sort of a child of quantum mechanics, right? If quantum mechanics had not been vastly successful, we would not be getting particle physics, because basically, that's Baji. If all the physicists of the 20th century kind of stomped on quantum mechanics and did not let that field to grow, we would not have these particle physics efforts that we have today. So it's a big success of quantum mechanics people of that century and going forward to see to get what you call the particle physics approaches of today. I know a little about Einstein and the theory of relativity, E equals mc squared. Yes, we talked a lot about Einstein in the month of November in our live streams. So if you missed our November live streams, Einstein is hugely featured in those ones. Cute kitty, early bird gets the worm. Good to see you again. Thank you. So basically, particle physics, we didn't touch upon it too much when we were talking about the 20th century stuff, because it's really more of a recent thing. It's more of a 21st century thing. And then particle astrophysics is basically doing astrophysics with particles other than visible light. So traditionally, astronomy and astrophysics have been done with visible light. Just our naked eye can look at the stars in the sky. Most of them are actually galaxies. But when you look up and you can see what's in the sky, that's visible light. So our eyes can only handle visible light wavelengths. There is light in other wavelengths, such as gamma rays or X-rays or microwaves or other wavelengths, and we can't see all these wavelengths. We can only see the visible light. And pretty much when you use the wavelengths of light other than visible light in order to do astronomy or astrophysics, that too is actually part of particle physics or particle astrophysics. Because, for example, especially if you're using light with wavelength shorter than visible light, like gamma rays are very tiny wavelength light. They're very high energy light waves, and they have tiny wavelength, as in they're more like a particle than they are a wave in terms of light. So at that point, doing gamma ray type of astronomy is sort of under particle astrophysics. As well as particle astrophysics can also be done with things like neutrinos, cosmic rays, just entirely other particles, completely other than light as well. So we talked about that. We actually introduced particle astrophysics and what are the different particle astrophysics type of experiments and things like that in my previous live streams. Today we're going to cover the topic, my favorite transients, my favorite event in the sky are actually gamma ray bursts. We're going to cover that today. So this is going to be chapter 5 of my thesis, and my thesis is called Studies in Particle Astrophysics. Let me just make sure that that is exactly the right that is actually what I called it. Sometimes oh my god. Go to my abstract. Okay, yeah, my thesis is called hi Grimace, hi Diegost, happy new year, happy new year. So my thesis is called Studies in Particle Astrophysics with the Anita experiment. You can actually, I cannot wait for the supernova of Betelgeuse. Oh my God. Yes, Betelgeuse. I think it's Betelgeuse, something like that. But yeah, absolutely, me neither. So we started talking about my thesis, and we kind of went through the first chapter, which is sort of an introduction to particle astrophysics and an introduction to the various experiments and energy regimes and things like that for particle astrophysics. Now, today we're going to talk about gamma ray bursts. Gamma ray bursts are basically what was a big motivation for me with this thesis, because they are natural particle accelerators. You know, just like we have the LHC, the Large Hadron Collider, things like that, where we have human-made particle accelerators. Think of that, but in the sky, existing naturally. So that's what we're going to talk about now. What happened to just looking up at the stars and believing whatever you wanted to? You could always still do that and learn about gamma ray bursts. So we'll get started now. Introduction to my favorite transients, gamma ray bursts. Gamma ray bursts, so you might wonder, what are gamma ray bursts? So don't worry, we will cover everything about gamma ray bursts in this particular chapter. So worry not. In fact, I have to grab a drink. I need to get a drink of water actually. So let me just give you this so that you know that's what we're about to talk about, and I'm just gonna get a water and come back. Hi, Suji. I'm very parched. So I'm super excited because I feel like we haven't had a proper physics live in a hot second. Like, I think my last couple lives were just kind of like hanging out, and I know a GRB can be deadly if it hits Earth, you mean? Okay, so let's get started. I can't wait. All right. Yay, gamma ray bursts. So you'll love how we actually first discovered gamma ray bursts. Does anyone have any guesses on how we actually discovered gamma ray bursts? It actually has to do with the Department of Defense. So they were not discovered in a very astrophysics-y kind of way. So some people might know this story, actually. Hi, Reese. The atomic bomb. No. So the atomic bomb was more in the 19 late 1930s, 1940s time period, middle of the 20th century. This is more recent than that, so more closer to the end of the 1900s, or not really the total end of it, but the atomic bomb is also a defense type of thing. This is not quite, but yeah, it was. I gave it away. I thought maybe you. It comes out of the heart of distant galaxies where supermassive black holes. So, sort of. So, gamma ray bursts are very far away, typically, but actually, supermassive black holes are at. There is a supermassive black hole even at the center of our own galaxy. So, you don't have to be in a very distant galaxy to have a supermassive black hole. We have one. But we don't have a gamma ray burst in our galaxy. That would be a lot. I'm not for sure, but it has to do something with Nikola Tesla. Nikola Tesla? Not quite. But yeah, any other guesses? But yeah, no, good inputs from you guys. We have a supermassive black hole, Sagittarius. Sagittarius star, actually it's called Sagittarius star, at the center of our own galaxy, our local black hole. So that's not quite, you don't necessarily need that. But anyway, okay. But you're right that gamma ray bursts do happen rather far away. They're definitely extragalactic, as in we don't really have them going on in our own galaxy, which is probably a good thing, because they're extremely big explosions. They involve extremely big explosions. So okay, perfect. Okay, yeah, no, good. All right. Let's look at this introduction. Gamma ray bursts are the most luminous transient events in the observed universe. So they are the most luminous transient events. So what does transient mean? Transient means that they're temporary. They're not something that is there and it just keeps on happening for a very long time, but more like a transient event. Right? But they're the most luminous. When they occur, they outshine an entire galaxy. That's how much luminosity a transient event like a gamma ray burst can emit. Gamma ray luminosities of gamma ray bursts are of the order of 10 to the 52 ergs per second, which can be compared to the 10 to the 33 erg per second emitted by our sun. So our sun's energy output is 10 to the 33 ergs per second. A supernova is 10 to the 41 ergs per second. And a whole galaxy is something like 10 to the 45 ergs per second. And here's a gamma ray burst, which is the order of 10 to the 52 ergs per second. Now a gamma ray burst, it's a short duration. We will talk about the specifics of all, the durations of a gamma ray burst, but it's short, but for the time that it is occurring, it basically outshines an entire galaxy. First discovered in 1967 by the Vela satellites. Let me take a clip of this. First discovered in 1967 by the Vela satellites, flown by the US Department of Defense, gamma ray bursts continue to intrigue and puzzle scientists to this day. However, research in the past decades have revealed much about them, including that they are extragalactic in origin, isotropically distributed, and that they come in at least two populations. So that's the thing. So they were basically, during the Cold War, they were discovered by the US Department of Defense, by the Vela satellites flown by the US Department of Defense. They picked up on these gamma rays basically, and they thought, oh my gosh, is this something that, some country of interest is doing? But actually they turned out to be a natural event. But yeah, those are the main points. They're extragalactic in origin, isotropically distributed, as in they're not necessarily, they're not specifically coming from a specific direction in the sky. They can have an isotropic distribution, and they come in at least two populations. Gamma ray bursts are classified as long if they last for greater than 2 seconds, and short if they last for less than 2 seconds. So for 2 seconds, the gamma ray burst outshines an entire galaxy. We'll get into more details of like, there's actually an afterglow and all that stuff, but basically they're transient events. So it's not like once this gamma ray burst happens, you can observe it at that same intensity for many, many minutes or days or whatever, although there is a part that we can observe later on at a different wavelength. But for those very short periods of time, depending on the length, if it's greater than 2 seconds, it's called a long gamma ray burst or a long GRB. If it's less than 2 seconds, it's called a short GRB. Long bursts are associated with the collapse of massive stars or hypernovae. So these are just supernovae that are really, really big. So like massive stars collapsing, probably when these massive stars collapse. So you were right. Someone said, I think it was Stephen, who said that they might become black holes. So basically, gamma ray bursts are not a black hole yet. Basically, massive stars collapsing, producing a supernova, hypernova type of situation, ultimately might collapse to a black hole. But before that point, this gamma ray burst phenomenon is happening. This transient event is happening. So the long GRBs are associated with the collapse of massive stars or hypernovae. And short bursts are associated with mergers of binaries composed of neutron star, or neutron star black hole. So depending on which gamma ray burst, sometimes you could also have the merger of neutron stars, as well as a neutron star and a black hole, or a black hole and a black hole, and that is going to be associated with the short gamma ray burst. In fact, we have evidence of this because we picked up on gravitational waves from a short GRB, and that actually gave us evidence of the fact that short gamma ray bursts are in fact associated with neutron star, which is very I think gamma ray bursts happen when a black hole swallows a star. No, so we just spoke about the association. So long gamma ray bursts happen when a massive star collapses. So it's a part of its death. So when a star collapses on itself because it has run out of nuclear power and it's collapsing on its own gravity, we get something called a supernova. If it's a huge event, we might even call it a hypernova. So that's just a supernova, but bigger. And during such a supernova, we can have something like basically a long gamma ray burst. Short gamma ray bursts are associated with something like a neutron star merger. So this would be a binary of neutron stars finally collapsing onto each other and producing a short gamma ray burst, as well as it could be a neutron star black hole combination or a black hole combination that's merging. So so I think sort of yeah. If you meant a neutron star, then yeah, sort of something like that would be a short. So there's different categories: long gamma ray bursts versus short gamma ray bursts. If it was the end of the world, what? In August of 2017, for the first time in history, multi-messenger observation. Listen to this. This is just what we talked about. In August of 2017, for the first time in history, multi-messenger observation of a short gamma ray burst was performed by the LIGO, Virgo, and Fermi collaborations, confirming the association of short gamma ray bursts with a binary neutron star merger. So by the way, I was in grad school at this time. And when this result came out, that was the first confirmation of the association of neutron star merger with a short gamma ray burst. Before that, it was simply theorized that short gamma ray bursts are associated with neutron star, or neutron star black hole mergers. But now we actually had confirmation. So we call this multi-messenger. Hi, Ben. Happy 2025 to you and your simply adorable cat. Thank you. Thank you so much. Happy New Year. Happy New Year to Ben. Hello. So multi-messenger, as in we get the light in terms of gamma rays. We got the gravitational waves in terms of in this case we picked it up with LIGO, Virgo, and all that. And we might even see, actually we'll talk about it later, we might even potentially see neutrinos. Fuji. No. How about no? Nope. Let's not do that. Okay. Okay, so I'll say that again. In August of 2017, for the first time in history, multi-messenger observation of a short gamma ray burst was performed by the LIGO, Virgo, and Fermi collaborations, confirming the association of short gamma ray bursts with a binary neutron star merger. So a binary of neutron star, neutron star. So this is the first confirmation that when a binary neutron star merger happens, then that is two neutron stars that were spiraling towards each other merges, it produces a short gamma ray burst. This was the first actual evidence of that. This marked the first observation of a messenger other than photons from a gamma ray burst, because generally all we had measured from a gamma ray burst is the gamma rays, right? In order to understand the physics of gamma ray bursts and to probe it with other things, we would need other messengers, and in this case we got gravitational waves from them. Indeed, no other messengers or particles have been known to come from gamma ray bursts, although theories predict that gamma ray bursts are environments where particles could get accelerated to the highest energies. So you can see now how gamma ray bursts would be sort of a motivation of particle astrophysics, or the neutrinos that I was looking for, because they are natural accelerators of particles. The detection of gamma ray burst neutrinos would provide unambiguous proof for hadronic acceleration in these cosmic explosions, and could also explain the origin of the cosmic ray flux at ultra high energies. So because gamma ray bursts are so far away, they're very extreme environments, right? They're very extreme, natural, accelerating environments. And we have sort of theories for what might be happening, but the only way to confirm these theories is to actually measure certain things from these gamma ray bursts. So for example, that thing I was mentioning, the excitement about getting the neutron star merger evidence, getting the gravitational waves as well as the gamma rays from that same event, tells us that, okay, yeah, this is confirmation that neutron star binary will give you short gamma ray bursts, and that's good. But then there's other questions also about gamma ray bursts, about that particular type of environment. For example, there could be hadronic acceleration happening. So this is the hadrons within that. It's a particle physics-y type of thing, but basically whether or not gamma ray burst environments will accelerate particles in a certain way or not, it's not confirmed. And it's not like gamma ray bursts are happening like right in our neighborhood. So we would need these types of evidences, and the more measurements we can make in multi-messenger type of way, whether that is gravitational waves or cosmic rays or neutrinos or actual gamma rays, the better. That's the more we have of different types of evidences from the same phenomenon, the more we would be able to tell exactly what these types of environments are doing. Okay, so the detection of gamma ray burst neutrinos would provide unambiguous proof for hadronic acceleration in these cosmic explosions. So they're also called cosmic explosions, various names of gamma ray bursts, and could also explain the origin of the cosmic ray flux at ultra high energies from gamma ray observations alone. So just observing the gamma rays, which is light. Theorists have hypothesized that regardless of the nature of the underlying source or progenitor, so progenitor meaning like that, either the star that's dying or the neutron star merger or whatever, gamma ray bursts are produced by the dissipation of the kinetic energy of a relativistically expanding fireball. Protons may be Fermi accelerated in this dissipation region to energies greater than 10 to the 20 eV. Interactions between fireball gamma ray photons of energy around 1 MeV and accelerated protons of energy around 10 to the 15 eV could lead to photomeson production of pions, which upon decaying would result in an accompanying burst of 10 to the 14 eV neutrinos. So this is actually a whole theory that some of these gamma ray burst theorists have come up with. And so if we saw neutrinos in association with gamma ray bursts, that would be like a huge confirmation of all this theory behind how gamma ray burst fireballs work. So that's why basically the gamma ray burst, especially at those high energies, because remember I was working on a particle astrophysics experiment looking for very high energy neutrinos, and getting neutrinos that are that high energy, you need the specific type of event which would actually make that type of neutrino, right? So that's why I was after these things. I was looking at them and trying to understand gamma ray bursts better, because they would be the type of environment that might potentially make those very high energy neutrinos. So now we will talk about the gamma ray burst emission. Steven says, love your kitties. Thank you. Okay, so gamma ray burst emission. Gamma ray bursts are characterized by a two-part. Hi. Oh, wait. I can't see your name. Hi, Kayla. Hi, how are you? Gamma ray bursts are characterized by a two-part emission. So there's two parts to a gamma ray burst emission, okay? Prompt and afterglow. And I will tell you already now that a lot of people only care about the prompt emission of a gamma ray burst. They don't care about the afterglow, but we will talk about the afterglow. You will see how the afterglow can be very important for us, for this particular work. But most of the time when people say a gamma ray burst of this length or whatever the time duration, they actually mean the prompt, okay? So gamma ray bursts are emitted during the prompt. I care about your afterglow. Oh, thank you. Hi, Suji. Suji mama. Suji's coming here. Gamma ray bursts are emitted during the prompt emission. Gamma rays. So gamma ray burst. Hi, crazy sick wine. Hello there. Brilliant, beautiful. Hope you're having an exquisite new year. Yes, thank you. Thank you for joining. You're just in time for gamma ray burst emission. So basically, gamma ray bursts are characterized by a two-part emission, prompt and afterglow. Gamma rays, so the gamma rays, which is the light of the wavelength of gamma rays, is emitted during that prompt emission period, followed by softer and softer photons, such as X-rays, UV rays, and so on. So gamma rays are like the hardest photons, as in they're very high energy and very small wavelength. If you have, say, softer photons, meaning that they will have slightly larger wavelength and softer frequency, as in lower frequency and lower energy. So like, because gamma rays in the light spectrum, gamma rays are like the most hard photons, as in they're very high energy, very short. Thank you for the kisses. Suji mama. Hi, Suji mama. Gamma rays are the hardest photons, highest energy, smallest wavelength, highest frequency, and pretty much all the other spectrum light is lower energy than gamma rays. So even X-rays, UV rays, those are all lower energy. So gamma rays are actually emitted during the prompt emission part of the gamma ray burst, whereas the next parts would be the afterglow. So even if you see like X-rays during the afterglow, that's basically going to be the afterglow, not the prompt, okay? So gamma rays are emitted during the prompt emission period, followed by softer and softer photons, such as X-rays, UV rays, and so on, during the afterglow emission period. As discussed in section 5.2, which is what we'll discuss in a bit, neutrinos are predicted from gamma ray bursts following an opposite spectrum to that of photons. So basically, where the photons are higher energy, in that particular phase of the gamma ray burst, the neutrinos will be opposite spectrum. So if you have higher energy photons coming out, you'd have the lower energy neutrinos coming out. If you have lower energy photons coming out, you'd have the higher energy neutrinos coming out, is the hypothesis. And this is what I was going to basically leverage for my neutrino search from gamma ray burst. So I ended up designing a search, and then I didn't have time during my thesis to actually complete the search, but that's the idea of it, and it's also a good review on gamma ray bursts, which I'm covering now. So, as discussed in section 5.2, neutrinos are predicted from gamma ray bursts following an opposite spectrum to that of photons. In other words, harder and harder energy neutrinos with time. The type of emissions from a gamma ray burst is summarized in figure 5.1. So let me show you this figure. So this will make it very much more obvious. So see how I'm basically saying that energy here is on the y-axis. It's sort of a cartoony kind of figure. And then time is on the x-axis. And see how there's prompt right here between 0.2 and 20 seconds, and then few minutes to a few months can be part of the afterglow. And you have energy in the y-axis going all the way up to like 10 to the 18 eV and more. And you have the gamma rays coming out, being emitted mainly during the prompt phase, along with high energy neutrinos. But then in the afterglow period, you're expecting ultra high energy, so even more high energy neutrinos, along with light that is falling spectrum, so X-rays, UV rays, optical, radio, something like that. So that's sort of the idea, which is that as you get softer and softer photons, meaning down from gamma rays, you get X-rays, UV, optical, radio, but the neutrino, which will be sort of the complementary particle coming out of gamma ray bursts, potentially, because I don't think we still have neutrinos from gamma ray bursts yet as an observation. So that's why it's still potentially a source of neutrinos, but we don't know. Either way, we will learn about gamma ray bursts today. But that's sort of what we're expecting. So the prompt emission, thank you, Stephen. The prompt emission is typically between 0.2 and 20 seconds long. Note that the prompt emission can occasionally last for several hundreds of seconds, as was seen in the case of a 5,400 second long GRB that was reported in a particular paper. So basically, you can have some very long GRBs as well. There was apparently this 5,400 second gamma ray burst, but pretty much depending on for how long you're getting that prompt gamma ray emission is what you would call was the length of the prompt emission part of the gamma ray burst. So depending on which gamma ray burst, you might even have a much longer. So what I found is that gamma ray bursts have a lot of diversity. They're not just like, oh, they're all kind of similar. No, it's very diverse. There's a lot of diversity in gamma ray bursts, and they're not a simple topic. So once again, the prompt emission is typically between 0.2 and 20 seconds long. So that's more like typical, right? So like if somebody asks, what's a typical gamma ray burst prompt emission time period, then it's going to be between 0.2 and 20 seconds long. And that's already sort of a range, right? But then we're saying that, note that the prompt emission can occasionally last for several hundreds of seconds, as was seen in the case of a 5,400 second long gamma ray burst. So you're saying me being in Georgia, I'm in Boston. Very interesting. Gamma rays are astounding. Yes. So the afterglow emission time period for gamma ray bursts is even more diverse. So the prompt emission has some diversity already, as we're seeing, but the afterglow emission period, like after the prompt, you still continue to get X-rays, UV rays, optical, maybe even radio waves from a gamma ray burst. We would call it an afterglow emission. And for that, I learned that it really like depends on how long you're observing. At some point, the people who are observing with certain instrument might just say, okay, we're done observing this one, we don't care. And so the afterglow emission period sort of stops because you stopped observing. So there's a lot of diversity in the afterglow emission time period. And this is something that I also thought. So in astronomy, it really depends what people care about. If they don't care about pointing their instrument and looking at a certain object or event for a very, very long time, and we're talking in this case, the afterglow could be for months. If they just stop observing, then you don't have the data anymore from that particular event. So, there's also limited resources for all these types of observations. So things like that. Fuji's probably gonna push something off the counter. The afterglow emission time period for gamma ray bursts is even more diverse. The afterglows can last from anywhere between a few minutes to several months. Swift scientist at the Mullard Space Science Laboratory, Matt Page, showed me the flux versus time plot of a gamma ray burst with afterglow observations in X-ray that continued over a year. So I actually went to the Mullard Space Science Laboratory in the UK. I worked at University College London as part of this thesis for a little while, and I visited Mullard Space Science Laboratory, and there were a bunch of scientists who were observing gamma ray bursts there. And they told me that sometimes the gamma ray burst afterglow is so long, like they basically just have to decide that, okay, we're going to stop watching this one. We don't have observation time for this particular source anymore. I love supernovas and black holes myself, but do love our planets and exoplanets that keep being discovered. Yeah. So anyway, that was interesting. So they watched one particular gamma ray burst afterglow observation in X-ray for over a year. Matt shared that eventually the observers decided to move on and assign observation time to other objects. So keep in mind that we might have limited information about the afterglow period of certain gamma ray bursts just because we don't have observation time assigned to these particular gamma ray bursts. But remember, we will see, and we already kind of mentioned that the higher energy neutrinos are expected during the afterglow. And so if you're looking for higher energy neutrinos from gamma ray bursts, you might want to keep that in mind. Afterglow records might not be available for a few other reasons. Sometimes afterglows are not observed at all, as no telescope is pointing at the object for follow-up in afterglow. So the absence of a record for an afterglow does not necessarily mean that there was no afterglow. Moreover, afterglow photons can get absorbed by dust and not be able to reach us. Thanks to my discussions with Swift observers at Mullard Space Science Laboratory for these insights. So Swift is an instrument for this type of observation, and there were a bunch of Swift scientists at that particular lab. Gamma ray bursts are interesting too, can be deadly to life on Earth if one strikes the planet. So anyway, gamma ray burst theory in the early days. So it's not that the gamma ray burst would strike our planet. We might, if we're pointing towards a gamma ray burst, we would hopefully pick up on the gamma rays and subsequent X-rays, UV rays, optical, whatever that comes out of the gamma ray burst. But gamma ray burst, you need a hypernova or a neutron star merger or a neutron star black hole merger to get a gamma ray burst. It's not like a gamma ray burst will strike us. They're not like an asteroid or something like that, if that makes sense. A gamma ray burst is an event in the sky. It's not so much an object that would be sort of coming towards us and striking us. It's more of a faraway event in the sky. Like you would need some big massive star's death, which would lead to a bigger than usual supernova called a hypernova. That would be one way of getting a gamma ray burst. Or you would have a neutron star binary, or a neutron star black hole binary, which are spiraling towards each other and collides finally, and that there's an explosion, and then that causes a gamma ray burst. So it's not necessarily something that would strike us, but we might pick up if we have the instruments in place and if we're pointing towards the right source. It is a source. So it's a source, and it's a source of gamma rays and maybe even a source of other particles like cosmic rays or neutrinos of higher energies that would be of interest to us, that we can probe, especially if we can measure with those other types of particles. If we're pointing at, and if we're looking at a gamma ray burst, for example, right? No, this is a good way to clarify. I'm glad you said something about that, Stephen. Like I said, I know very little about cosmology. This is more of an astrophysics topic, but yes. So basically, gamma ray bursts, what we do hope will strike us is the actual gamma rays. That's actually how they were discovered, right? So in that sense, we hope that our instruments that are in place for certain gamma ray bursts or certain sources that we're interested in do pick up on gamma rays, or in case of the afterglow, it might be X-rays or optical or radio waves or whatever. Or in case of neutrinos, like we have neutrino observatories that we have talked about in this topic, right? Like in the earlier parts of this thesis. And if neutrino observatories are looking for neutrinos coming from, say, gamma ray bursts, then that would be a huge sort of discovery that yes, you can even get these higher energy particles coming out of the gamma ray bursts, and that would help. Because gamma ray bursts happen so far away, we cannot easily probe them. It's not like we can go say hi to a gamma ray burst, sit next to it, and see what's happening inside of it, right? They're very extreme, explosive types of cosmic events, and so how do we probe them? And this is where the what we call multi-messenger astronomy or multi-messenger astrophysics comes in, where we probe these types of events with various things. You can do it with light. So if you pick up on the gamma rays coming from such a thing, then you say, okay, I saw some gamma rays. I have a gamma ray detector, and it was hit with gamma rays coming from a source, like a gamma ray burst, which is a natural source. You know, it could also be some human source. So you would make sure that that's not the case, you know, for this. Then say you're also ready with like X-ray detectors or UV ray or optical or radio wave detectors coming from the same source. And if you pick up on that later on, then that would basically prove out the fact that the gamma ray burst, you're getting a softer and softer spectrum of light coming from the gamma ray burst, as in gamma rays first and then softer photons like X-rays, optical, radio, right? Same way, what we're saying here in this chapter is that maybe these things could also make higher energy or ultra high energy or high energy cosmic rays and neutrinos. And if we are ready with those types of telescopes, which are picking up on cosmic rays and neutrinos, then we could learn something more about gamma ray bursts. We have already, because remember, we already kind of do multi-messenger astronomy with gamma ray bursts, because the moment we pick up more than one thing from a certain source, it's a multi-messenger thing. We already have gamma rays from gamma ray bursts. Okay. So we already have gamma rays from gamma ray bursts. We also have the gravitational waves picked up by LIGO, which is the Laser Interferometry Gravitational Observatory. We already have gravitational waves coming from neutron star merger. So basically, yeah. So basically, we already are in the realm. We're already pretty much doing multi-messenger astronomy when it comes to gamma ray bursts. So pretty much all if we could just get more types of messengers from gamma ray bursts, like if we also got cosmic rays, if we also got neutrinos, then we're very much making it a reality of doing multi-messenger astronomy. Geez, I leave for a few minutes and we get all the weirdos in here. Yes. How dare you leave us, Dora Dora? You have to make sure that the weirdos are under control. So basically this, and I wanted to mention, take a pause and mention this now, which is that multi-messenger astronomy is a new thing. It's not something we were able to do in the 20th century. It's not something that we were doing even maybe 20 years ago. This is a current thing. So we have spent a lot of time on the channel talking about, you know, modern physics in terms of sort of older stuff. For example, the 20th century is the last century. It's been some time, right? We established all of that so that we can talk about the stuff of today, which is what we're talking about now: particle astrophysics, multi-messenger astronomy. This is not something we could do before. I mean, we'd be lucky if we actually got just gamma rays from a gamma ray burst, let alone looking at the other parts of the spectrum from a source like a gamma ray burst and trying to understand, oh my God, so, okay, so first it does gamma rays, then it might do softer photons like X-rays, UV, optical. Like that tells us something about these gamma ray burst events and you know, the environments that produce gamma rays, because they're not close to us. There's not other great ways of knowing what's up with them. But now it's not just about light. We even can pick up gravitational waves from gamma ray bursts. And if we also picked up on the light part, the gamma ray part, or whatever else other part, then we are truly getting a multi-messenger kind of look at these exotic events in the sky, these cosmic explosions, which is very, very cool. That's the sort of thing we were not really able to do in the past because we did not have the instrumentation, the coordination, the collaboration that is needed, and the sort of focused collaboration that is needed in order to achieve multi-messenger astronomy. But that's really where we're kind of headed, where we would be able to probe these faraway events with multi-pronged approach, get the light from them, get the gravitational waves from them, get other particle from them, neutrinos from them maybe, right? Because again, those would give us other parts of the picture and tell us other things about the physics story within gamma ray bursts. Because remember I said something about the acceleration of particles. We'll get into it in just a little bit here. But basically, when you just, in these environments, there is more than just light, right? There's more than photons as part of these environments. There's more than gravitational waves as part of these environments. We know that these are cosmic explosions. Of course, we expect some kind of gravity waves from them because basically, when this big explosion happens, that whole space-time curvature, the gravitational waves that you would expect, it loses gravitational energy and it puts that out. And if we have a sensitive enough instrument on Earth or even a satellite of Earth, right now we just have Earth ones. We don't have the satellite ones put out yet for gravitational waves. But being able to see that, you know, that's another part of the picture. Same thing for the particles. These environments potentially, theoretically, hypothetically do a bunch of stuff with the particles in the environment as well. But we won't really be able to confirm that until we can measure as well those particles. And we would have to kind of do that, like sort of pointed in the sky. Like if the gamma ray burst is happening here, we want to be looking here, right? And we want to make sure that the gamma rays came from there and the other particle came from there and the gravitational waves came from there. We can't be looking over here, you know? So this type of like what we call more more directional and point source or source search. Basically, there's the types of search of particles from the whole sky or from whatever sky that you can see, right? Like for example, the South Pole Station, IceCube is a neutrino observatory in the South Pole. at the South Pole. So the biggest billion dollar neutrino observatory with the most number of high energy neutrinos measured is IceCube. They're still operating at the South Pole Station in Antarctica. So they look at the southern sky. Of course, they can see neutrinos that would go all the way through the Earth from the northern sky as well. But basically, there are searches for neutrinos, for example, that kind of look at, they don't really care about the direction that the neutrino is coming from. It's sort of like an all sky search, even though all sky might be a little bit of a generalization. And then there are searches that are more of a source search where you care about the direction. So something like gamma ray burst, if you were to prove out that your neutrino definitely came from a gamma ray burst, then you would need that multi-pronged approach. You would definitely at least want to be able to say that you definitely had the gamma ray coming, like you saw the neutrino at the same time when the gamma rays were coming from that particular source and during that particular time during which the gamma ray burst happened. Because remember, with gamma ray bursts, the nice thing is that you would also know in time when it happened. So that kind of helps as well, sort of. It's amazing how in-depth physics is, simply breathtaking, how it takes you to such unbelievable beauty within our existence and everything that surrounds us. Yes. Yeah, physics is yes, I love that about physics. The physical sciences really explain our existence in more depth. The most widely, so now we will talk about GRB theory. Okay, so even though we did not measure gamma ray bursts and all the different things one could potentially measure from gamma ray bursts until more recently, there are plenty of theories about gamma ray bursts because we started to see them. Of course, we discovered them in 1967, like we mentioned earlier. And because we discovered them and we've had them around for, well, a long time, at this point, 60 plus years or so, or is it 60 years? Someone do the math. How long ago was 1967? We've had gamma ray bursts for that long, and they somehow are still a bit of a mystery. And we will see why. It can be difficult to learn about them, so we will see. Actually, give me 1 second. Let me check on my... Oh, you know what? It's fine. It's all good. Whatever. Okay, we will talk about gamma ray burst. It's amazing. Oh yeah, I read that comment. Gamma ray burst theory in the early days. So this is gamma ray burst theory in the early days. The most widely accepted theory for gamma ray bursts endorses a relativistic fireball. So we'll talk about the fireball, but basically a gamma ray burst is a relativistic environment. Things happen very fast, things happen with a lot of energy. So it's not, you can't do non-relativistic in that particular environment. The observation of gamma ray bursts, of gamma ray photons, guided this theory. In fact, the observed photon spectrum was the starting point for gamma ray burst theorists. So it's not that the gamma ray burst theorists just woke up one day and thought that they will come up with a theory for gamma ray bursts. First, gamma ray bursts were discovered. Then people were like, oh my gosh, what are these things? Then we actually observed photons in the form of gamma rays from gamma ray bursts, or more of them. We also observed the photon spectrum. And then theorists got to work about, okay, how do we kind of explain this? So up until 1994, gamma ray bursts had been observed to emit photons in the energy range between a few keV and a few tenths of MeV. In 1994, however, a very energetic burst was reported by some paper that I cite here that emitted photons of energy up to 18 GeV. That's a lot for a photon. Other observations, such as by the Fermi Observatory, have confirmed this hardness of the photon spectrum from gamma ray bursts. It was argued that since observed photons from the gamma ray emitting region of the gamma ray burst do make it out to us, the optical depth in this region of tau gamma gamma must be less than 1. So now the optical depth, tau gamma gamma, is a function of the Lorentz factor, which there's a review on this by Waxman, the author. And thus, from tau gamma gamma, it was obtained that the gamma ray emitting region in a gamma ray burst must be moving with the Lorentz factor of greater than equal to 100. So some relativity math later, we have a Lorentz factor. Thus, the fireball model says that the gamma ray emitting region of a gamma ray burst is relativistically expanding. It was theorized that gamma ray bursts are produced by the dissipation of the kinetic energy of a relativistically expanding fireball. So it's an expanding fireball and it's relativistically expanding. And that's because we got some other math in place. Waxman, there's a bunch of papers by Waxman, Waxman. I cite them in my thesis. They have done the math. The Lorentz factor is greater than equal to 100. So it was theorized that gamma ray bursts are produced by the dissipation of the kinetic energy of a relativistically expanding fireball. The expanding fireball has regions of overdensity moving at different speeds. So basically, it's kind of like there's more matter and less matter. The expanding fireball has regions of overdensity moving at different speeds. When these regions collide, shocks are produced. So we will now get into these shocks. Particles are accelerated to relativistic speeds. The relativistic ejecta of a gamma ray burst may undergo internal collisions resulting in prompt emission, as well as collisions with the interstellar medium resulting in afterglow emission. So this is the interesting part. So depending on which region and the collision happening where. So again, I'll read that part. The expanding fireball has regions of overdensity moving at different speeds. So we get that. It's a relativistically expanding fireball, and there are regions of overdensity moving at different speeds. So of course there will be some collisions, right? Now, because all of this is happening relativistically, not only are there collisions, there are going to be some shocks that are produced because of that. And particles get accelerated to relativistic speeds. So it's almost like we don't need a human-made particle accelerator. This environment is a natural particle accelerator where there's these like relativistic expansion and shocks happening due to collisions and things like that. So now remember about the collisions happening in the different regions. Depending on if there's internal collisions, those actually will later on you'll see lead to the prompt emission. And if there's collisions with the interstellar medium, because this stuff is happening here, there's also the environment around it, interstellar medium, and collisions with that can result in the afterglow emission that we will talk about. So again, the relativistic ejecta of a gamma ray burst may undergo internal collisions resulting in prompt emission, as well as collisions with the interstellar medium resulting in afterglow emission. This afterglow will be important. We will talk about it. In these collisions, shock-accelerated electrons emit synchrotron and inverse Compton radiation in the form of gamma rays. So this is what causes the gamma rays. Because, we call them gamma ray burst, but really this is an environment doing all these types of collisions and shocks and things, right? So like how did we get the gamma rays? Why gamma rays, right? So in these collisions, because of the overdensity moving at different speeds, relativistically expanding, shock-accelerated electrons emit synchrotron and inverse Compton radiation in the form of gamma rays. So you can look those processes up. They're well understood. Thus, it was theorized that part of the kinetic energy of the gamma ray burst is a source of the observed gamma radiation. Like this is a lot of kinetic energy from all this expansion and such, right? So if you're basically losing some of that energy by basically losing the accelerated electrons emitting a bunch of synchrotron and inverse Compton radiation, producing the photons basically is one way of giving off that energy and losing that energy which is coming from the kinetic energy. It may be that the kinetic energy is converted to energy of electrons, comma, energy in magnetic fields and energy of protons. So we just don't know, but this is where we're hypothesizing. So basically we're saying it is theorized that part of the kinetic energy of the gamma ray burst is the source of the observed gamma radiation. It may be that the kinetic energy is converted to energy of electrons, energy in magnetic fields and energy of protons. So we have a review on this as well. I actually have a review about this that I published myself as well. No neutrinos are produced in the leptonic theory of gamma ray bursts. Basically, there are a couple different theories now that come into play. Depending on which theory it is, you will get neutrinos or not get neutrinos. So let's look at this. No neutrinos are produced in the leptonic theory. This is the leptonic theory. Now, lepton is a family of particles. Remember, in particle physics, there are 3 families of particles, broadly speaking: leptons, quarks, and bosons. I almost forgot. Leptons are something like the electron or something like the neutrino. Quarks are, of course, an example would be the stuff that makes up protons and neutrons, and bosons, an example would be something like the photon. So those are the 3 families of families of particles. In terms of gamma ray bursts, there are a couple of competing theories. The leptonic theory says that basically most of the kinetic energy of the gamma ray burst is assumed to go into energy of the electrons or leptons, and the electrons then emit gamma radiation in the form of synchrotron and inverse Compton radiation. There are no interacting baryons and no neutrinos produced in this picture. So basically, even though neutrino is actually also an example of a lepton, but this is basically, strictly speaking, saying that the energy is in the form, like all the gamma radiation is because the electrons, who are super excited and accelerated and all that stuff, will emit gamma radiation in the form of synchrotron and inverse Compton radiation, because turns out that to get neutrinos, you need a different type of process to happen, which we don't know whether it happens or not in a gamma ray burst until we see neutrinos from a gamma ray burst. So now we'll talk about that. So neutrinos are predicted in the hadronic theory of gamma ray bursts. So there are 2 competing theories. One is the leptonic theory of gamma ray bursts, which only allows electrons to be accelerated in a way that then produces gamma radiation from the electrons, because electrons, when they're so shock accelerated, oh my God, we're so excited, then they're not going to just stay that excited, right? They're going to give off synchrotron radiation and inverse Compton radiation, and you'll basically get photons out, and those electrons will then calm the frick down. And you hopefully, if we're looking, we will see the gamma rays coming from the gamma ray bursts. So that's what happens. That's why we get gamma rays. But if we were to allow something else to also happen, then potentially we would also get neutrinos. So what is this something else? This is the hadronic theory of gamma ray bursts. So the hadronic theory says that protons, remember, protons are called baryons. So baryons are protons and neutrons, making up, of course, ordinary matter in the universe. In the environment, which this type of gamma ray burst, where this is happening, of course, there are baryons in that environment. So what if we allowed the baryons to also be shock accelerated and doing crazy things? What would happen then? The hadronic theory says that protons are also shock accelerated in the dissipation region and may interact with photons of the gamma radiation. Now remember, we talked about this earlier in my thesis. Remember how if you actually interacted, if you had protons that interact with highly excited photons, remember what happened? You would basically produce some intermediate excited particles, which then basically leads to making neutrinos later on. So this is the theory in which neutrinos will ultimately come out of gamma ray bursts. So let's read through this. The hadronic theory says that the protons are also shock accelerated in the dissipation region and may interact with photons of the gamma radiation to produce pions. So pions are intermediate particles. They're unstable. They will not just stay as pions. They will become more stable particles. The hadronic picture allows for the production of neutrinos and is supported by Waxman-Bacall. So the 2 authors here that we're citing are Waxman, Ellie Waxman. Hopefully he's okay. Bacall, B-A-H-C-A-L-L. Waxman is W-A-X-M-A-N. Bacall is B-A-H-C-A-L-L. I think Waxman is still my LinkedIn friend, so hopefully he's doing all right. And Baukol, I think, is a more senior guy. The photon-meson interaction resulting in the intermediate delta plus of mass 1232 MeV is thought to dominate neutrino production in the work of Waxman and Baukol. So let me show you. Basically, this is saying a proton plus a photon will give us something called a delta plus. This is a very unstable intermediate particle of mass 1232 MeV, which will then give us neutrons and pions, or protons and pions. If it's a neutron and a pion, then it's a neutron and a pion plus. If it's a proton and a pion, then that pion will be a neutral pion. And then depending on, basically these pions are unstable and they will decay into muons and neutrinos, or electron, positron, and neutrinos, or even if it's a neutral pion, it will decay into gamma rays. A perfect example of the difference between a bachelor's in physics and PhD in physics. Love your passion for it. Oh, thank you. Einstein and Erwin Schrödinger would be proud. Oh, thank you so much. Thank you, thank you. So basically, you have seen this interaction already. If you saw my previous live, let me show you. This is what I'm talking about. That right there. Basically, a proton and a photon. And remember, we already have gamma rays in this environment. We know, we have proof of that because the whole thing started by getting gamma rays from gamma ray bursts. Basically make an intermediate particle called a delta plus particle, which has mass of 1232 MeV. This is very unstable. This is an intermediate particle. It's not going to stay as a delta plus. It's not going to hang out as a delta plus for very long. It will decay to make either a neutron as in the stuff that we know and love, neutron and a pion plus, or a proton and a neutral pion. If it's a pion plus, then that pion plus will give us a muon and a muon neutrino, and the muon plus will decay further into a positron, an electron neutrino, a muon antineutrino, and a muon neutrino, all regular stuff. You can look up how a pion decays and you'll get this sort of equation. You can look up how a muon decays and you'll get this sort of equation. If muons didn't decay, we would have more muons, right? But muons decay, and that's why we have electrons. They decay into electrons or positrons, depending on which one. And then, of course, we get more electrons. And then the pion plus, because you could have also made a pion plus, remember, as an option, and then that would decay into gamma rays. So either way, in this interaction, at the end, you have neutrinos, potentially, and more gamma rays. Now, we already had gamma rays, so we're not so interested in seeing more gamma rays, but potentially, through this hadronic acceleration, you could get neutrinos. Reese! Hi, Reese. Hello, everybody. Thank you so much for joining. Welcome to the live. Thank you, Crazy Sick Wine. Thank you, Reese. Happy New Year. So basically, the leptonic theory for gamma ray bursts says that the electrons are accelerated, and those accelerated, shock accelerated, just excited to the power infinity type of electrons give us gamma rays because they do synchrotron and inverse Compton. And you can look these processes up, basically ways to lose energy and give us gamma rays. And we know we pick up on gamma rays. So of course, probably there is such things happening. But the hadronic theory of gamma ray bursts tells us that what if we allowed the protons to also be shock accelerated? So not just the electrons, but the protons, if they're also shock accelerated, then they could also become very excited and interact with photons, give us an intermediate particle of the delta plus, which then decays to give us neutrons or protons, and then pions, and then the pions will give us muons, electrons, positrons, and neutrinos. And ultimately, you would get high energy neutrinos from this process. So according to Waxman-Baukol, the authors of this type of theory, approximately half the time the photomeson interaction of an accelerated proton with a gamma ray photon. So this is called a photomeson interaction, another name for such a thing. So this is the interaction between an accelerated proton and a gamma ray photon creates a neutron, and half the time a proton. So I mentioned how it can either make a neutron or a proton, right? So half the time it kind of makes a neutron and pion plus, and half the time it kind of makes a proton and a pion, neutral pion. When a neutron is created, it can escape the magnetic fields of the gamma ray burst into space, beta decay into a proton, and reach Earth as cosmic rays. So this is super important. The nice thing about creating a neutron is that it's neutral. So it can escape the magnetic fields of the gamma ray burst and go into space and beta decay into a proton. And by the time it's reaching Earth, it might be, just a proton, and basically we get it as cosmic rays. So that's super cool. We could get cosmic rays from a gamma ray burst. But of course, at that point, it might have changed. It might have bent around a little bit, and we might not know that it came from a gamma ray burst. Since gamma ray bursts are some of nature's most powerful accelerators, it is only natural to hypothesize that the highest energy cosmic rays observed with energy around 10 to the 20 eV might come from gamma ray bursts. It was theorized by Waxman-Beckal that the neutron created in the above reaction was a source of cosmic rays. To ensure that gamma ray bursts could be the source of both cosmic rays and neutrinos, the following was assumed, which is basically sort of these optical depths of proton, proton, neutron, proton, proton, photon. Neutron, photon is around 1. It's a theoretical sort of assumption. This way, protons needed to interact at least once in the source with photons before they could leave the source. So basically, they're doing some math for this type of source, right? Let me finish. I'm going to read your comment. This way, protons needed to interact at least once in the source with photons before they could leave the source. The charged pion would decay to produce neutrinos, and the neutral pion would decay to produce more gamma rays. Because basically, remember, if you had even one interaction of a proton with a photon in that particular environment after being accelerated, you would make, let me go back and up and look at my own equation here. Even if you had one interaction between a proton and a photon in that environment, you would make either the neutron plus the pion plus, or the proton plus the pion 0, or the neutral pion, right? So even with one interaction, you're still gonna get neutrinos at the end, because there's just no avoiding the decays of those things. So the charged pion would decay to produce neutrinos, and the neutral pion would decay to produce more gamma rays, which we were already getting gamma rays. The mean pion energy was 20% of the energy of the proton producing the pion, according to Waxman et al. This energy was roughly evenly distributed between the pion plus decay products. So each neutrino coming out of this process would have roughly 5% of the energy of the original proton. From particle kinematics, the following key relation between observed photon energy E gamma and the accelerated proton's energy EP at the photomeson threshold of the delta resonance was obtained, which is that E gamma times E proton is approximately 0.15 minus 0.2 GeV squared gamma squared, which is the Lorentz factor now. Inserting in the above equation a typical observed gamma ray energy of 1 MeV, because we kind of know that the gamma ray photons are around 1 MeV, and the Lorentz factor of 100, Waxman-Beckal found a characteristic proton energy of around 2 times 10 to the 6 GeV, or 2 times 10 to the 15 eV, which would produce neutrinos of energy around 10 to the 14 eV. So this is how we determine, see, it's so step by step. We first figure out the photon energy, and we had an estimate for the Lorentz factor. From there, we also figured out the the proton energy. And we also know how many neutrinos come out and where the energy has to go. We know it's five, because depending on how many, each will roughly get around the same, so 5%. And so from the proton energy, you can deduce the neutrino energy that you're expecting. So in the hadronic picture proposed by Waxman-Bacall, these high energy neutrinos result from internal shocks within the fireball and accompany the prompt emission of gamma rays. And we would expect a neutrino energy of around 10 to the 14 eV. Now remember, these are theoretical types of predictions for the energies. So experimentally, you'd have to see like what you get and kind of constrain the theory or update it. But that's what the theoretical sort of prediction was and what they were expecting. They were basically thinking that if you got high energy neutrinos from the prompt emission part of the gamma rays, that because of this math I just mentioned, it would be around 10 to the 14 EV. Ultra high energy neutrinos are thought to result from collisions of the expanding fireball with its surrounding medium. So now remember that there's also the afterglow, right? We didn't talk about that yet in terms of the neutrinos. Basically, the same kind of collisions that were happening inside the fireball, that's the prompt emission, and that gives us the prompt emission type of photons, protons, and neutrinos. What about the expanding fireball colliding with the surrounding medium? That also leads to certain shocks and collisions and things like that, and we will see what happens there. So, inserting equation 5.2.1. Now, what did I do there? Oh, I see. So equation, where is 5.2.1? Which equation am I talking about? Who wrote this? Who wrote this? Did I even number my equation correctly? Oh, you know what? It's just that energy equation. It's okay, whatever. Doesn't matter. So basically that same kind of math that we just did for the prompt emission photon and proton, we're gonna do for the afterglow. So a typical afterglow photon energy. So that same energy of the photon that we had assumed to be around an MeV for the prompt emission, because the prompt is gonna be more energetic. We're saying that a typical afterglow photon energy is around 100 eV, and the Lorentz factor is still 100. Neutrino energies of order 10 to the 18 eV are found. Because basically in that energy, remember, it's basically energy of a gamma or energy of a photon times an energy of a proton is equal to some stuff, right? So if the sum stuff is about the same, then basically the energy of the photon and the energy of the neutrino are kind of like oppositely related. Like in the parts of the gamma ray burst where you would get more energetic photon, you're supposed to get less energetic neutrino. And if you have less energetic photon, you should get higher energy neutrinos. So this was my point, which is that we don't generally look for ultra high energy neutrinos, or sorry, high energy neutrinos even from the afterglow of a gamma ray burst typically, but we should. I was basically proposing that we design a search for ultra high energy neutrinos utilizing the afterglow. I'll be right back. I ordered sushi. That sounds good. I kind of want some sushi now. So we'll continue. Ultra high energy neutrinos are thought to result from collisions of the expanding fireball with its surrounding medium. Inserting an equation, which we just talked about, that energy equation, the product of the two energy photon times proton energy thing. Because remember, the energy of the photon times the energy of the proton equal to some stuff is important because the neutrino inherits the proton's energy. Remember how we said that if you spread the energy among the neutrinos are about equally, the energy of the neutrino is going to be around 5% of the proton's energy. So as soon as you kind of know the shock accelerated proton's energy in the gamma ray burst, you have an idea for the neutrino that you should be expecting from that particular proton, because we know that that proton, after doing some business, will eventually produce neutrinos, because the stuff that that energetic proton will produce upon interaction with the photon, all that stuff is unstable and it's going to decay. And the ultimate product of those decays are all going to be neutrinos. So as soon as you know the proton energy and you have an idea for the photon energy, because you have observations of the photon energy, because that's how we generally historically picked up on gamma ray bursts. It's the photons that we see from the gamma ray bursts, right? The light energy. When you insert all that in the equation, you might get an estimate for the proton energy. And as soon as you do that, you also get your neutrino energy estimate. So I feel like that's so interesting, because the neutrinos, which are also leptons, are not coming from the leptonic tree way of getting the particles, but the baryonic way, the hydronic way of getting the particles from the gamma ray bursts. So I think that's wonderful. Anyway, ultra high energy neutrinos are thought to result from collisions of the expanding fireball with its surrounding medium, because the collisions don't just stop here. They also keep on going with the surrounding medium. Those medium things are like, oh my God, we're getting, like shock accelerated, colliding with the stuff from the gamma ray burst, right? So inserting all that into the math, a typical afterglow photon energy of 100 eV and Lorentz factor gamma of 100, neutrino energies of around 10 to the 18 eV were found, which is basically the ultra high energy regime. This is why I was excited to think that we might get ultra high energy neutrinos from the afterglow part of the gamma ray burst. But do we look for neutrinos in that particular period? Do we give enough time and effort to that particular period of the gamma ray burst? That is a different question. It was theorized that protons accelerated in the dissipation region of a gamma ray burst may interact with photons of the prompt emission, as well as photons of the afterglow emission, producing charged pions that may decay into high energy and ultra high energy neutrinos. We know that at those energies, when photons and protons interact, you make those intermediate particles, including pions, which will make neutrinos depending on the type of pion, right? I mean, you could either have a charged pion or a neutral pion. The neutral pion would make gamma rays and the charged pion will make neutrinos, end of story. So the point is, you should get neutrinos in this particular way. Waxman and Balcall predicted that a kilometer squared neutrino detector should detect around about 10 to 100 neutrinos of energy around 10 to the 14 eV per year, correlated with gamma ray bursts. So they thought that this should be about the rate at which we should observe these types of neutrinos. In Waxman, Balcall showed, in another paper, they showed that cosmic ray observations set a model independent upper bound to the intensity of high energy neutrinos produced by photomeson or PP interactions in gamma ray burst sources of size not much larger than the proton photomeson or PP mean free path. The upper bound is as follows. It's basically E nu squared phi nu of less than 2 times 10 to the negative 8 GeV per centimeter squared per second per steradian. It's just a limit. Post the study of gamma ray burst afterglows, it was predicted by Waxman Balcall in yet another paper, that the expected detection rate of ultra high energy, which is basically 10 to the 17 to 10 to the 19 eV, mu1, they thought mu1 neutrinos, because the neutrinos have like 3 flavors. They thought that this rate was around 0.06 such neutrinos per kilometer squared per year over 2 pi steradians. So very small rate. And then they further showed that the upper bound mentioned above is robust and cannot be evaded by invoking magnetic fields, hidden fluxes of extragalactic protons, etc. So basically, they did a lot of work to come up with these upper bounds of like how much detection rate of such neutrinos we should be expecting from gamma ray bursts, given that gamma ray bursts are obviously, not the most common thing either. but they do support, logically speaking, they support shock accelerated protons and a type of environment in which these neutrinos could be getting produced. And if they are, if we are sensitive to that rate, we should be picking up on such neutrinos. But we'll see if we can, measure and experimentally get them or not. The detection of gamma ray burst neutrinos would provide unambiguous proof for hadronic acceleration in these cosmic explosions, and could also explain the origin of the cosmic ray flux at ultra high energies, which is nice. So the origin of the cosmic ray flux at ultra high energies, that's the cosmic ray flux is something that has questions as well, like why we have certain flux at certain high energies, like are there more sources for such cosmic rays, is also a question. The above theoretical predictions for neutrino fluences from gamma ray bursts were put to the test by experimental searches for high energy neutrinos. We discussed the relevant experimental work and results in the following section. So these were all the theories about gamma ray bursts and how and why you should expect certain particles being produced, what type of processes would make them, and at what energies. So this is all the theory of that. And then we would actually do the experimental searches to look for them. And actually, now that I'm thinking about this, when I was writing this thesis, we did not have neutrinos from gamma ray bursts. It was basically not discovered yet, but I should check. There might be neutrinos from gamma ray bursts that are picked up by ice cube, actually. So you know what? I'm looking at the rest of this chapter and seeing what is basically covered. So I basically, for the rest of the chapter here, I don't know if I'll get into the experimental side of things today because I've been talking for a while, so I might take a break and read your comments. But basically, this is what we discussed, all the theory stuff up to now, like a theory of why these things would be produced, how are they produced. But after this, I get into the experimental searches for ultra high energy neutrinos from gamma ray bursts, and I cover, let's see, I did gamma ray burst neutrino search versus diffuse search. So I mentioned what is the difference between a source search and a diffuse search. Then I mentioned first gamma ray burst search by Anita. So I worked on this experiment called Anita, and in 2011 we had a paper of the first gamma ray burst search by Anita. So I talk about that. Then we also did the first gamma ray burst search by Ara. This is a scaring radio array. Another experiment in 2015 we published on the gamma ray burst search by Ara. So I talk about that next. And then I talk about some current theories. And then I wonder if we got an ice cube neutrino from a gamma ray burst sort of closer to, or maybe even on the day of my defense. So I should double check. There might be a neutrino that ice cube saw. If they did, then I don't want to miss it. But basically, Anita and Ara had not really found any neutrinos from gamma ray bursts, and they ended up placing constraints on the theories. Because if the theories predicted certain number of neutrinos or certain flux of neutrinos from gamma ray bursts, and the experiment doesn't see that, then basically you can say that we can place a certain constraint on your theory. But for next time, I'm going to double check whether ice cube, which is another experiment, ice cube picks up on high energy neutrinos, not ultra high energy. So I think there still might not be any ultra high energy neutrinos that we've measured from gamma ray bursts, but ice cube may have high energy, like prompt emission type of neutrinos. If they have that, I'm going to double check and make sure that I tell you the right thing. But that might have to be something we cover next time. So give me 1 second. Let me take a brief couple minutes to look for something here. So I don't know if they saw. Dor says that was one heck of a monologue, but very infrared. Really? Are you putting kettle on? Must be time for a cuppa. I really should. I want to make some hot chocolate with you guys. Was it a monologue? Well, this is my thesis. Reese, how are you? Haven't seen you in forever. Wishing you a fabulous morning. Thank you, Neeraj. Hello, namaste, hi. Crazy Sick Wine is saying, I'm applying to Caltech, going to give it another try before I get too old. I want to double major in math and physics, particularly experimental quantum physics, PhD eventually. Double major in math and physics. I know a lot of double majors in math and physics. Basically, if you're talking about undergrad, then there are so many sort of overlapping classes between math and physics majors. You almost have a math major when you do physics in undergrad. So that makes sense. What interests you more, the theoretical side or experimental sides? I'll be right back. I ordered sushi. One heck of a monologue. Oh, thank you. Thank you. Thank you. It's supposed to be right, not a criticism at all. Thank you. You're oh, thank you. Ati sundar hai aap. Oh, thank you. I'm okay. My sister gave birth on Christmas Day. I met him today. He's beautiful. Did you have a nice Christmas? Yes. I birthed a cat on. No, I'm just kidding. All my children are born. They're cats. What did I do on Christmas? Oh yeah, I got Malaysian food with my friend in Chinatown in Boston. So we started partying Christmas Eve. We went out. First we got Nepali food and drinks, chatted, all that stuff. Then we went to Chinatown on Christmas Day because yes, where is my firstborn child? Hello? Baba. Fuji. He's getting into trouble, my firstborn, as we speak. Then we went to Chinatown on on actual Christmas Day. It was very nice. Boston had lots of nice lights and things like that. And we saw so many people out and about looking for food because nobody wants to cook on Christmas Day. And the people who like celebrate Christmas Day more traditionally will stay at home and not go out, right? So a lot of places were closed. Fuji baby. A lot of places were closed. And then we were like, okay, we will go to Chinatown, and I'm sure that there will be Christmas Day food in Chinatown. So we went there. I birthed a cat. Yes, we went out Boxing Day. I got a bit drunk. Which one is Boxing Day? Have gained weight. Okay. I tidied all the trash from outside, a takeaway, because it was a mess. Oh, the day after Christmas Day? 26th. Okay. Boxing Day is 26th. I tidied all the trash from outside a takeaway because it was a mess. They didn't appreciate it, surprisingly. Oh, goodness. Why not? Ice cube high energy neutrino detection. I was gonna look up whether Ice Cube saw any gamma ray burst high energy neutrinos or not. We have all gained 300 pounds. I took all the rubbish into the takeaway for them. I don't weigh myself every single day, if that's what you're asking, Neeraj. I took all the rubbish into the takeaway for them to put in their bins, and they told me to get out. Oh no! I know, right? Tossers. So I was hoping to find out. Ooh, that's what it is. On the day of my defense, Ice Cube saw a high energy neutrino from an active galactic nucleus. So, not quite the same thing. That's what it was. I knew that there was, so, I wrote my thesis and then you defended a bit later. And on the day of my defense, literally as I'm defending, this new result came in. So it's not part of my thesis, which is why I felt bad. And I wanted to look it up. Ultra. So there's definitely, so I think on that day, we basically got a high energy neutrino from an active galactic nucleus, which is not quite the same thing, but whatever. Okay. Fuji, could you please stop? Okay, give me 1 second. I'm gonna get I think I'm gonna make some hot chocolate. Will you guys stay on? I think I need to get a drink, and then I'm gonna read about the Ice Cube results. Cats are smashing the place up. Yes, they are. Also got kicked out of a pub because my sister's boyfriend was vaping. Wow. I'm here for another hour. Oh, thank you, Dora. Thank you so much. So the summary of today is we talked about gamma ray burst theories, the theories that would lead to production of these photons, as well as potentially neutrinos via the protons and things like that. And now we will next talk about some more things, a little bit more current measurements, and see where we're at with the neutrino measurement by Ice Cube. But I didn't get into the experimental results part from my thesis yet today. So we will pick up from that next time, but we'll still continue today with some other exciting things from the internet on measurements, because basically at the time of writing my thesis, the status was that we didn't really see any neutrinos from gamma ray bursts, or at least confirmed from gamma ray bursts, and we were pretty much placing constraints for neutrinos from gamma ray bursts. If there was some prediction by a theory, basically we were putting limits because we didn't find any. But literally on the day of my defense, like when I'm defending my thesis, this new result comes in, which is that Ice Cube is one of the it's like the biggest experiment pretty much in the neutrino world. They found a neutrino correlated with an active galactic nucleus. Now I forgot, I was trying to remember what type of source was it again, because it's not in my thesis, because it literally isn't, the result is coming out on my defense day. And they asked me about it during my defense. My advisor, I remember they asking me this question because it was still, coming out on my defense day. It doesn't have to be in my thesis, but they still asked me about it. And they were like, okay, if this is what's happening, what does defense day mean? that's the day you defend your thesis and get your, like you pass or fail your PhD exam. That's when you would get your, you basically become a doctor that day. Yeah. So basically you, as part of your doctoral degree, you write a thesis and then you defend your thesis on the day of your defense with your full committee. Sometimes even the public can be present if you allow them. And so you defend your thesis and they can ask you any question. So even though, yeah, so part of your thesis was concurrent with the release day of said data. That's one heck of a turnout. Yeah, so I am defending my thesis and I'm basically saying in my thesis, as you'll find out on when I started chapter 5 of my thesis today with you guys, which is basically focused on gamma ray bursts as a source potentially for neutrinos. So it's obviously relevant for, you know, particle astrophysics. If we get neutrinos from gamma ray bursts, then we can study gamma ray bursts with the help of neutrinos. It's part of that whole particle astrophysics story, right? So I wrote a whole thesis on it, and I talked about these various experimental searches we did and how we didn't really find any gamma ray burst neutrinos yet at that time of writing the thesis. And basically I was saying that we haven't yet found them, so we're placing limits on theories that predict gamma ray burst neutrinos. Basically, we're saying it's either too hard to find them, or basically they're more rare than we thought, and we can't actually find them. But then, lo and behold, on the day of my defense, there's this new data that comes in where they've seen a neutrino from an active galactic nucleus. So it's a little bit of a different thing, but that hadronic acceleration thing that I was talking about earlier, it's basically a confirmation of that. So because I studied gamma ray bursts, I was able to still answer the question, and like because I was studying the, you know, the hi Goodwill, I'm in love with you, thank you. Because I was studying the processes that may cause the production of high energy neutrinos from gamma ray bursts. Because I studied that, I was like, and they don't care if the data point comes in on the day of your defense. On the day of your defense, they can still ask you any question from physics, and you should be kind of able to answer if you're going to get a doctorate in physics. So they're like, oh, this data came out and they weren't even sure what it meant, because not everybody is an expert on gamma ray bursts, you know? So they're like, oh, this thing came out. What do you think of that? Like, what do you think that means? And I'm over there, I'm like, what? Did they find one? Like, it's a big deal to me. It's a big freaking deal to me if they found a freaking high energy neutrino from an active galactic nucleus, or any source for that matter. Because at that point, we basically, you'll see how I'll cover this more formally from my chapter here later on, maybe tomorrow. But basically, we had only seen neutrinos from diffuse searches, from like sort of like general searches, from like all sky surveys of neutrinos of this and this and this energy. Oh, we found some. You know, Anita basically hadn't found any. Ara hadn't found any. And I was interested in source searches, like getting a neutrino from a particular source and basically proving that there are these natural particle accelerators where these hadronic processes could happen, where the proton could be interacting with the photon to then make pions, which then makes neutrinos. And this whole thing was not yet confirmed until the one data point came in on the day of my defense. So I was like, dumbfounded when they're saying, because I've been preparing like my laptop and my everything, my talk. Like, you also have to give a talk on your defense day. Basically, on your defense, you give a talk, you defend your thesis, you summarize it in a talk, and you're giving the talk, and they're asking you any question they want. It's like 5 people. It's like a 5-to-1 ratio, like where there's 1 me and 5 professors grilling me. about anything in physics, and they can ask any question. And one of them or two of them had seen the data come in, and I was like too busy to know that it had come in. So that's why I knew there was something that's not in my thesis, but it did happen like on the day of my defense. So there's definitely more data out there than is in my thesis. So that's also something that I'm trying to tell you, is that the thesis is not the most current document on the findings of various neutrinos. Okay, so you guys stay with me. I'm gonna make some hot chocolate. I've talked too much, I know. Hi Goodwill, hi Doral, hi Crazy Sick One. Yes, please eat your sushi, enjoy, and stay with me. I gotta put the phone on charge and make some hot chocolate, and I'll return to the discussion with you guys. But I am so charged up now because I just remembered that active galactic nucleus data that came in on the day of my defense. Wow. That's my baby. My baby came out that day. So I birthed a neutrino that day. I didn't really, but it felt like I did. Let's look at this. It's on Reddit. It's on Reddit. Just amazing. Oh, this is just amazing. Okay. Okay, guys. All right, guys. Hello. Shitting on stars and cats. Yes. She's an absolute proton. That's true. Goodwill got it. If I'm a proton, then I will make a neutrino. That's very true. Okay, let me put this on charge because the phone's low. Let me put you guys on charge, and then I need to use the bathroom, and then also I'm gonna make some hot chocolate, and we will sip it together and continue this amazing chat. Thank you guys. Is it charging? Someone call me fat. How dare you? How dare you? Wait, what is happening right now? Phone, you're here. Yes. Charging, charging. Charging, charging. Good. 17%. Hopefully gets more percentages of charge. Excusez-moi, I'll be right back. Suji. No suji. Okay, I might give you a snack. I don't know. I haven't decided. Oh my gosh. I remember. Oh my gosh, I have to use the bathroom. Okay. BRB, guys. morning, pineapple. I'm back. I just get distracted sometimes in the bathroom. Well, I go to the bathroom, but then I like look at something else. Then before I know it, it's been longer. It's quiet as a mouse. Welcome back. Hi, Goodwill. The heat of anti-immigration. What? I work from home, finished around 2:30 a.m. Now I'm having a bath. Almost 5 a.m. Yeah, he is in the UK. Scarborough. Isn't that right? Scarborough. Scarborough. Am I saying it right? Good morning, pineapple. Looking very good, very nice. So I got distracted. I saw a message from somebody. I got distracted. I had a whole feminine situation. Now I'm back. Oh my gosh. Good morning, pineapple. Oh my goodness gracious. Oh, sorry. I'm so sorry. He is from Belgium. I am. Who doesn't use their phone on the toilet? Yeah, I tend to go unnoticed in life. An internet add-on has noticed you. It can only go up from here. Hopefully. Look at you guys. You did all the detective work. Okay. Thank you. Belgium. Belgium. He's from Belgium, everyone. I have a thing for the UK. I love it there. I love the trains. That's why I remember. It's from Belgium. From Belgium. Okay, I still have to make hot chocolate, you guys. But your comments are really entertaining. It's quiet as a mouse. Bliss. Anti-immigration. Britain was always good at taking territories and controlling them. What? Also, people using there and there incorrectly makes me want to breathe fire. Fire. It's sun and fire. It's a YouTube chat. You thought that was a while in the bathroom? That was nothing. I'm suspecting she solved world hunger or cracked dark matter. Oh, thank you. Oh, Dora, thank you for your patience. You're in Boston, right? Yeah. Me? Yes. Reese, you can now be anonymous with me. You now live in Belgium. Yeah, he's Belgian. Like Hercule Poirot. Like Hercule Poirot. Like Hercule Poirot. Belgium police. That's where he's from. Alright, everybody, I will now make the hot chocolate and then I will continue the chats. I will continue the chatter. Continue the chatter. Hello, my children. Come have snacks. I'm so happy because I talked about gamma ray bursts. We will continue experiment tomorrow, but we will finish up the chatter about gamma ray burst / related neutrino measurements tonight. Chatter. Oh yeah, it is like 5 in the morning for the Belgians. Good. Early hours. If you're joining at this point and feeling confused, you can go back in the time in the video and look at the gamma ray burst discussion that we have been having tonight. The detective, the baguette version of Sherlock. Really? I'm hungry now. Yeah, man, get you some breakfast. So feel free to go in the this way direction to see the full discussion on the gamma ray bursts. in the back direction. Oops. Hi. Hi, Flowey Slum. Hi, Fuji. Dog panting noises? What? No, that was just me washing a cup. Maybe I'm a dog. Kitty cats are over here, chilling. 1 cat, 2 cat, 3 cat. Hi, my babaloo. Hi, baby. If there's a dog, it might be me, not them. like a dog. You guys are so nice. You stay and chat. Thank you so much, everybody, for joining and chatting. And thank you so much, everybody who is joining and feeling confused. And you can go into the live in the, past and see our discussion on gamma ray burst. Dog panting? What? To be honest, I don't know what I'm doing. Oh, you know what? I should have made some boiling water. Now that we know about the Belgium thing, I want to do a Belgian accent. I want to pour some water into my cuppa. And stir really well. I finally get to hang in the chat for once. Usually I have to disappear. But Reese, remember you're Belgian. That's what I'm doing. Wink, wink. Remember? You're Belgian. So this is Belgium now. Reese is from Belgium. And they talk like this. Now I'm licking a knife. You know what? I don't know why I didn't make the water boiling thing happen. To be honest, I forgot. After a certain point, I just lose my mind. You never know what's gonna happen. Hi, Fuji, Suji, Baji. Hi, my babies. Hi, my wonderful childrens. So, yeah, there's been kind of like some stuff going down. Oh, by the way, Reese, congratulations on becoming an uncle. I'm a bona fide Belgionardo. Have you made that chocolate shroud yet? Yes, I'm currently making it in the microwaves, like every quantum particle. Exactly. I'm a quantum particle myself. 30 more seconds. So, congrats on becoming an uncle. Any other births of any kitty cats, dogs, or humans? She had to have a C-section. He's wonderful, bless them. Aww. Well, I was a C-section. A cesarean. Didn't really come out of nowhere. I had to be taken out. I don't believe in struggle. C-section. Indeed. Indeed, I am as well. Oh my god, this chocolate is extremely hot now. Or the mug is, I don't know. Is it off? Yes. Off, yes. Off, yes. Off, yes. Off, yes. Off, yes. I probably removed myself and went in a quiet room. What do you mean? You removed yourself from the birthing, you mean? That makes sense. Not everybody's allowed to be there, right? Wait, what is happening? Ah! Where is thing that I was using to put, no, I mean from the womb. I probably removed myself and went in a quiet room. Oh, from the womb. Yes, 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 yes. Indeed. I'm that antisocial. No, he's very social here on my lives because it's a safe space for interesting people. You've been talking with us for a while. Janita, hi. You guys are normal. Most people are strange. We are interesting. We talk about interesting things. I am an anonymous anime character on the net. Well, we are very special. This is a very special live stream. We talk about all kinds of things, cats and physics, cats and books, hashtag. You have a good sense of humor, though. That's good enough. Me? I try. I try. So let me continue my search here. Cats and physics, yes. Cats and physics, cats and books. I'm tired. I've been tired for a few days because someone I know is kind of like going through something. And so we've been kind of going through it. So yeah. Okay. Friend, but you know, closer to family. So Ice Cube Neutrino Observatory. The hunt for neutrinos from gamma ray bursts. So this is Ice Cube's website. In 2012, shortly after the Ice Cube neutrino, so this is, I'm reading from a website which is run by the Ice Cube experiment, which is the world's largest astrophysical neutrino experiment or measuring detector, basically. Bless them. Thank you. Yeah. No, I hope that things resolve very soon here for this person. Yeah, thank you. The hunt for neutrinos from gamma ray bursts. In 2012, shortly I had to pick up my best friend up from hospital. Oh no, what happened? Hopefully they're okay. I'm sorry guys, I gotta go. Goodwill, we will miss you, but Goodwill, you can always look at this video when it posts and leave us a comment. Thank you. Love you, City. You're the best. Thank you, Goodwill. Thank you. See you next time, Goodwill. And yes, please. Thank you so much. When this video posts, if you could leave us a comment, that would be amazing. And then you can catch up with the rest of the video as well when you see it later on. Okay? Thank you so much. Really appreciate it. Really appreciate everyone participating and staying on the live for as much as, whatever time you can. Thank you so much. It's kind of gross, but sounds awful. Hey now. Hi, Crazy Sick Wine. Hello. How are you? Yeah, no, hopefully your best friend feels much better. Any kind of problem, health-wise, I hope that, gets better. In 2012, shortly after IceCube Neutrino Observatory was completed. So IceCube was completed shortly or around 2012. I guess that makes sense. Which year did I start grad school? 2013. What does that emoji mean? I'm chilling, enjoying hanging out with you. Thank you. Yes, please continue to hang out with us. Thank you so much. Thank you so much. Indeed. Oh, it's a salute. Okay. So shortly after IceCube Neutrino Observatory was completed, the IceCube collaboration announced in Nature. So Nature is the name of a journal. An important and unexpected result in neutrino astrophysics gamma ray bursts, GRBs, which were one of the two leading candidates for sources of high energy neutrinos and cosmic rays, did not report any neutrino excesses. Since then, IceCube has continued to improve the analyses, which now include real-time searches, and to establish ever stronger limits on the contribution of gamma ray bursts to the observed diffuse neutrino flux. So it's a Belgian thing. Okay. So basically the thing I mentioned earlier, which is that if you look for, say, a certain type of neutrino in your search, say you're looking for gamma ray burst neutrinos, which would be from a source. So it's not an all sky survey looking for neutrinos, but more like from a source. Say you look and you analyze your data and you don't find any, you're basically going to have to place a limit or a constraint on the theories that predict a certain flux of neutrinos. Like if the theory said that you should have found gamma ray burst neutrinos to this level of rate or something and you don't, then basically you can then back down. You can then in turn tell the theory, hey, I'm putting a limit on you. Whatever you said is not quite right. So your prediction needs to get updated, basically. So stuff like that continues to happen even when you're, say, looking for these neutrinos and not finding any. And of course, you can also do a diffuse neutrino flux type of search, and that should also kind of place some limit because the diffuse neutrino kind of assumes that, well, some of it would be contributed by the gamma ray bursts, right? Gamma ray bursts are a source of neutrinos, and a diffuse search means that you don't care about the source per se, but you should still find the neutrinos that would be coming from gamma ray bursts as part of that. The IceCube collaboration, in collaboration with Fermi Gamma Ray Burst Monitor, so this is the GBM. Yes, there has already been some work on searching for neutrinos from gamma ray bursts, and we're talking about that right now. And we will continue to talk about this next time as well. So since then, IceCube has continued to improve the analyses, which now include real-time searches and to establish ever stronger limits on the contribution of gamma ray bursts to the observed diffuse neutrino flux. The IceCube collaboration, in collaboration with Fermi Gamma Ray Burst Monitor, presents a new study. I want to put my feet up. Presents a new study that now includes neutrino emission up to a 2-week window before and after a GRB detection. The results of these analyses also show no excess of neutrinos, but provides us with new limits on neutrino emissions from extended timescales. These results, recently submitted to the Astrophysical Journal, once again constrain the contributions of gamma ray bursts to the astrophysical neutrino flux seen by IceCube and provide a means for testing current gamma ray burst models some of which have been excluded. So basically, as they continue to search for gamma ray burst neutrinos and don't find any, they can basically even exclude certain models and theories that would predict these neutrinos. So it's still like progress, but at the same time, it's a little bit, like, what the frick? Why aren't we getting any neutrinos from gamma ray? It's another question. Hi, Riri. Hello, how are you, Riri? So over here is such a plot. They show the constraints. Gamma ray bursts are considered to be caused by the collapse of, so this is another little review, this time from IceCube. So this is considered this to be like another little source for you guys for this discussion. I like your bear and doing good. Oh, this bear? Yes. Thank you. His name is Edward. I've had this Edward bear since teddy bear since I was a child. Thank you. I am drinking some hot chocolate. Gamma ray bursts are considered to be caused by the collapse of massive stars or due to compact binary mergers and are among the most energetic sources in the universe, which makes them great candidates for sources of ultra-high energy cosmic rays and neutrinos. So because they are some of the most energetic sources in the universe, that's why they would actually be great candidates for sources of ultra-high energy cosmic rays and neutrinos. Like, why not, right? So that's why this is worth investigating and worth exploring. Until now, IceCube had performed several searches for neutrinos correlated with the gamma ray emissions from the main phase, also known as prompt gamma rays. So remember I said that the prompt emission time is when you see the harder photons, that is the higher energy photons, but that is kind of when you would get sort of the lower energy neutrinos, but these neutrinos are still high energy and should, actually, these are the neutrinos that IceCube should be sensitive to as far as the predictions go. And remember that IceCube is sensitive to high energy neutrinos, not ultra high energy. That's okay, Riri. Bye. See you next time. Prompt gamma ray emission is hypothesized to be the output of a relativistic fireball emerging from a plasma of electrons, photons, and hadrons that are accelerated to the highest energies. The same environment would produce neutrinos, which could potentially be seen by IceCube and would have temporal and spatial correlation with gamma ray emission. So temporal means in time and spatial means in direction. So like if you're saying a neutrino is going to come from a gamma ray burst, it better be coming from the same direction in sky as the gamma ray burst, because gamma ray burst gives you an angular in the sky, or what you would call spatial correlation. Like if a gamma ray burst happened here, you don't expect the neutrino from here, you expect the neutrino from there, right? And neutrinos point straight back to their source because they're not charged. They wouldn't have been, deflected on their way. So the nice thing about gamma ray bursts is that they give you this temporal as well as spatial correlation with the gamma ray emissions. Like the same time during which you saw the gamma ray emissions, as well as the same spatial correlation during which you saw the gamma ray emissions is when you would expect to see the neutrino emission. And you can always, look at a certain window. Basically, it looks like they start maybe like a week or two before the gamma ray and after. Detecting neutrino emission correlated, and of course, remember, this type of search is in the analysis level. So it's not like you have to predict when a gamma burst will happen and then look. You look And if you have data in the temporal and spatial correlation with the gamma ray emission, you go back in the data and you analyze around the gamma ray burst time period. And also you make sure that you're not getting biased. There's like ways to do sort of a blind search for the gamma ray burst neutrino. Those types of things too we can talk about later on, but they would basically still have to do certain cuts and stuff in the analysis to make sure that they're getting that temporal and spatial correlation. Detecting neutrino emission correlated with gamma ray bursts would have established these gamma ray sources not only as sources of neutrinos but of cosmic rays as well. Yes, that's the other thing, is that if you get neutrinos from gamma ray bursts, you should also get cosmic rays. However, gamma ray bursts have been known to produce gamma ray emissions before and after the main burst, known as precursor and afterglow emissions. So I didn't talk about precursor too much, but basically there's even like a precursor part, which is before the prompt, and then there's of course the afterglow emission, which we talked about in my thesis. And there's a possibility of neutrino emissions from these phases as well. These extended emissions have motivated the analyses presented in this paper, which look for statistical correlations between neutrinos and gamma ray bursts up to 14 days before and after the start of the prompt phase for gamma ray bursts in the period between May 2011 and October 2018. Oh wow. IceCube members, in collaboration with 2 Fermi GBM team members, have performed 4 different analyses, each one based on slightly different assumptions. In total, 2209 GRBs were examined. So that's over 2,000 GRBs that they examined for this analysis. Wow. Okay, extended TW. So here in the extended, so now we're going to talk about the analysis that they did in a few different parts, okay? And it's not a lot of text, so this should not take that long. So extended version of the analysis that they did. Here, basically what they did was researchers examined 10 time windows around each gamma ray burst, ranging from 5 seconds before and after the gamma ray emission to a window of 15 days from a full day before to 14 days after the emission. So that's the extended search. Precursor or afterglow. In this case, each gamma ray burst was fit with a precursor time window ranging from the beginning of the prompt phase up to 14 days prior, and an afterglow time window ranging from the beginning of the prompt phase up to 14 days after. GRB precursor. The time windows were taken to be the time intervals during which gamma ray precursor activity was observed from gamma ray bursts. Stacked precursor. The time window of each gamma ray burst was taken to be 250 seconds, covering the time period in which gamma ray precursor activity is seen. And now drum roll. None of the 4 analyses, so I mentioned 4 analyses here that IceCube has done: extended, precursor, afterglow, and precursor, and then stacked precursor. 1, 2, 3, 4. Yeah. None of the 4 analyses found evidence of a correlation between neutrino events and gamma ray bursts, which is kind of a bummer. So none of these analyses found evidence of a correlation between neutrino events and gamma ray bursts. And so then they placed a limit. So a limit looks like basically it's a curve on a plot, which shows fraction of diffuse flux versus neutrino emission duration. And so they put like a 90% confidence upper limit on the contribution to the quasi-diffuse neutrino flux from the total population of long gamma ray bursts for different durations of precursor or afterglow neutrino emission in any model predicting neutrino emission above the red line for the respective emission window is rejected. So they reject any models that is above a certain level of the flux for certain neutrino emission duration because they didn't see any. Measurements were used to set new limits on the contribution of cosmic Measurements were used to set new limits. So this is the type of result you get when you don't actually find the neutrino. Measurements were used to set new limits on the contribution of cosmic gamma ray bursts to the ice cube neutrino flux and test different emission hypotheses. Prompt neutrino emission from gamma ray bursts is limited to less than 1% of the observed diffuse neutrino flux, and precursor afterglow emission from long gamma ray bursts on timescales up to 10,000 seconds is constrained to 24% of the total diffuse flux. This is not the end of gamma ray burst searches in ice cube, though, because non-detections do not demonstrate that gamma ray bursts are not high-energy neutrino sources. In fact, these searches are expected to continue with the proposed ice cube Gen 2 detector, which will have increased sensitivity to observe populations of gamma ray burst sources. So they're saying that they will make their detector more sensitive and keep looking, because not finding any does not mean that gamma ray bursts are not sources of these things. Each new limit helps in testing old and new hydronic models. Because remember, the hydronic models came up with the predictions, and certain details in there might have to be updated, basically. Gamma ray bursts examined to date allow for more segmented searches that look for neutrino emission from specific subclasses of gamma ray bursts, such as choked gamma ray bursts. These are interesting events that result from a core collapse supernova and that are not electromagnetically bright. And yet, those sources should also produce high energy neutrinos. Yeah. Gamma ray bursts are rapid, transient sources that can emit neutrinos in a window that lasts from milliseconds to thousands of seconds. Bursts shorter than 2 seconds are known as short gamma ray bursts and tend to have a harder energy spectrum than long gamma ray bursts. We know that. Current efforts to look for real-time emission that can motivate multi-messenger observations are now in the process of implementing an extended TW analysis technique, and we'll look at gamma ray bursts from 2018 to now. On top of those, offline comprehensive studies should be performed every few years to study the significance of the collection of gamma ray burst results. And this was posted on July 1st of 2022. So as of July 1st, 2022, IceCube did not find any neutrinos correlated with gamma ray bursts. I know in my thesis, we didn't really find any neutrinos correlated with gamma ray bursts with our experiments that are the radio Cherenkov way of looking for neutrinos. So far, as far as I know, we don't really have a positive answer to the hunt for neutrinos from gamma ray bursts, but we're trying. And we have placed limits. So that's sort of the story right now. That was this episode. We talked about gamma ray bursts. In particular, we talked about multi-messenger astronomy, where you do astrophysics with particles other than visible light, including gamma rays, other types of light like X-rays, as well as completely other particles such as cosmic rays or neutrinos. And particularly, we talked about gamma ray bursts as an important sort of source, an interesting event in the sky, a very explosive event in the sky, which happened kind of far away from us, which could be important or interesting sort of extreme sources of neutrinos. We know we get gamma rays from them. We even get softer photons from them. And we would like to kind of probe them with a multi-messenger type of approach. So that's what we have been covering in this particular live stream. If you go back, you will see the full discussion more and more. I wanted to read out this IceCube result for you guys because IceCube is the biggest, most well-funded detector for astrophysical neutrinos in the world, and they exist at the South Pole Station in Antarctica. And they come up with a lot of these analyses, and I wanted to just make sure that they didn't find something from gamma ray bursts more recently. But there was that active galactic nucleus neutrino that they found on the day of my defense, which I thought was very funny. But as far as the gamma ray bursts go, it looks like we don't have any yet. So sort of the hunt continues, and our understanding needs to be further kind of updated as we keep on going and make detectors that are even more sensitive, and so on and so forth. So that was that discussion. I just wanted to touch upon the ice cube results, and it looks like it's a pretty recent one, 2022. You know, as more grad students come in and do their PhDs, they will analyze more data, and we will get more papers out. But 2022 is not too bad. So looks like as of a couple years ago, they published on a lot of data, a lot of gamma ray burst data, and still didn't really find a neutrino that correlated. So, Sharky Chills, hello. Hi. So thank you so much for being here. Thank you for chatting. Thank you for being in the live. If you're joining and you want the full discussion on gamma ray bursts, then just keep going back and see the full discussion. Thank you so much for being here and enjoying, or sorry, chatting in the live. People came in at the very end. Yes, people came in at the very end. So if you're coming in now or you just came in, make sure to just go back into the live. I think you can still drag the cursor to go back towards the front of the live, towards the beginning of the live, and still catch the full discussion. So no worries if you're coming in later. You didn't miss anything. You can still see the full video. Thank you so much. I'm just going to finish up my hot chocolate and sit with you guys and just kind of take a breather, breathe out. And I'm glad that we covered gamma ray bursts today. It's my favorite transient, and it's my favorite sort of potential source of neutrinos. So I covered it in my thesis, and I wanted to share that with you guys as well. Definitely thank you. It was brilliant as always. Thank you, Crazy Sick Wine. Thank you so much. Yay. Yay, 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 yay. Do you guys have work tomorrow? Oh, wait. I think you told me you're going to take this week off, right? Doro Doro? Okay, good. I'm going to try to go live again tomorrow during the day so that we can cover more. But yeah, thank you so much for being here for the gamma ray burst discussion. Sadly, yes, 9:30. Okay. Light days. Oh, the days at work are lighter? That's good. So Crazy Sick Wine, you said that you're looking to get into Caltech. Is that for undergrad or for grad? I'll work like 2 hours at most. Okay, good. But yeah, back to it next week, full on. Well, if you miss my lives, depending on when I go live, because I think a lot of my lives will probably still be in the evening. So you guys should be able to join, hopefully. But if you miss anything, then they always get posted. So I still look forward to all your comments under the videos of the live streams if you miss one in real time. Thank you so much for that. Grad, hopefully. Oh, nice. So are you thinking about doing grad school in physics then for Caltech? At Caltech? I have a friend who went to Caltech for physics, actually. I can ask her for any tips or tricks for your application. Also, I guess applications would have been due like sort of in the fall, right? For next fall? Is that what you're doing? Let me share the live. Yes, I've been putting it off for 2 years now, so I'm hoping I could. I'm 28, so time is of the essence. Better now than never. You can do it. Yeah, 28 is still very young. And if it's for grad school, then you'll still be. That's still young for grad school. Yay, Dorodoro. Yeah, I can ask my friend. She did astrophysics like me. Like we did different types of astrophysics. So she did more of a theoretical. I think you were asking before, and I, was waiting to answer. I think you were asking, I think if I remember right, you said Caltech. So good luck for that. Good luck with the applications. And then you said theoretical or experimental. Well, I personally did particle astrophysics experiment. That's what I did. I think, whatever you want to do, a PhD. So if this is for a PhD, it's really up to you, right? You'll figure it out. You'll see which one you want to do, where you have interests, I did a number of rotations though. Like my PhD ended up having a few different rotations. It felt very difficult back then because I was like, what am I even doing? Will I even have a PhD if I keep on doing the rotations and changing labs, basically? But it actually made me a little bit more, it made me more well-rounded in the different topics than maybe some other people. So most people, they go in, they select a lab to do their PhD with, and they kind of stick with it. But I tried out quite a few different ones. Well, I was hoping for MIT, but I prefer the weather here in California or Harvey Mudd College. Boston is not that cold anymore. We get a lot less snow than we used to. So don't be afraid of MIT weather. Besides MIT, the buildings are all connected. So you barely have to be outside. And if you're doing a PhD in physics, it's not like you'll spend a lot of time outside. Unless, well, it depends on the experiment. If it's an experiment that's outside, then yeah. But mostly the labs are inside, and that's where you'll be for your grad. So I don't know how much the weather really matters, but you're right. You should probably enjoy your life. We're still live. And we covered gamma ray bursts. You should probably enjoy your life during your PhD. And I guess that's better in California. So you're right. Caltech it is. It's too hot there though, right? My friend who went to Caltech, she complained that it's too hot. It's like a desert. And we like trees. So we like Boston. We like the East Coast with its ocean and trees and things like that. My PhD was in Ohio. Too much. Too much Midwest. And too much rain and cloudy and snow. I prefer Boston. I guess if he lives there already, then he likes it. My unsolicited opinion, never liked Cali. I like Cali, I like visiting. It's too much like a desert in places though. But the weather was nice and cool compared to where I'm at. Has perfect weather, honestly, but I could never live there. Are you in New Mexico? Are you in Texas? It's hot there. You don't have to say. I just like guessing. I live somewhere on Earth. Good. Good, good, good. So yeah, I would look at Caltech's. I figured it's the South. Where it's hot. Somewhere south. Yeah. 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 So I would check Caltech's program, like the department, and see like what, what type of things they have, and if you like the types of opportunities you would get at Caltech in terms of your, research. Yes, I'm still deciding though, because I love traveling to the Hamptons in New York, and I've been to Boston several times, enjoyed, and went to many parties there. Yeah. You have beautiful nostrils. Oh gosh. Hello, people. Sorry, didn't mean to show you my nostrils. But thanks. What? That's hardly an odd thing to say on this live. We have seen it all. This live chat has everything. Yeah, I don't really have like a phone holder thing where I would put the phone, I don't know, at this level maybe. Maybe I should. I kind of like myself at that level. True. You had racism, sexual. Yeah. That's after putting a couple people on timeout. I probably should get a phone holder thing that lets me put the phone up here so that I have a better angle. But I don't, and I don't want to pay for that. If somebody wants to sponsor the phone holder thing, let me know. Oh, and I should say, Spotmart has sponsored this pendant. Thank you, guys. The nostrils comment. Well, yeah, because it reminded me about the angle. It's fine. It's not. It's fine. Now I'm like holding this stupid phone up. It's fine. Whatever, man. Whatever. Thank you, Spot Mart, for the pendant. I need to get on. I need to actually include their link and stuff in my description. So did you party for New Year's Eve? Yes, at home. I'm not all self-conscious. I'm just... Yes, so I had a party here in my house. My friends came over. Now I'm self-conscious because you're calling me self-conscious. Doro Doro. My friends came and then they ordered pizza for us. I still have leftovers pizza. I have leftovers pizza. I didn't really party hard. I can't really party hard. It gives me a headache. Ooh, and I had wine too. Yes, same here. I am still recovering. Haha. Had too much wine. Yeah. No, it's all good, Dora Dora. I'm enjoying with you guys. Actually, on a different live, you should bring up the nostrils comment. It'll make me laugh. If you see things getting too serious, Doro Doro, you should say nostrils. Do you like Chicago deep dish? Not really. I'm a New York style. I'll do my best to remember. Yes! I'm more of a New York style pizza person. Not really a deep disher. If I'm being honest. Honest. Is there cat hair in this? Just checking. Right? New York style is better, right? I don't really want too much messing. Yeah. Deep dish is just wild. It's a freaking casserole. Yeah. I don't want a casserole. I want a pizza. I want to be like, ah. I want to hold a slice that's like almost falling apart and just hum. You know? So are you gonna work from home tomorrow, Doro Doro? Can you work from home on architecture? I am. Oh, good. So you don't have to go anywhere. That's great. Okay, then you should definitely join my live. Sometimes, depends on the job and time. But yeah, this whole week will be from my house. Ooh, a house. How nice. Good. Great. Lou Malnati's deep dish was delicious. Only Chicago pizza I like. Okay, guys, are you ready for this? Crazy Sick Wine. I have not been to Chicago, but yes, I prefer New York always. Yeah, same. New York for pizza, but I haven't been to Chicago yet. And I spent a very long time in the Midwest. But I was in grad school, so I didn't have much of a life there. But I've actually never been to Chicago, and I should probably change that. And good to know about the pizza. Lou Malnati's. Okay, I will look for it. Should I get it there? Classic. New York, Detroit, Chicago. Yeah, okay. No, I think I would tend to agree. I didn't really get pizza in Michigan. Sachi mama! Oh my baby! Oh my baby! Hi Sachi! Suji is asking for more attention. Come Sachi! Come! Are you baby too? You're a baby! Wine has me wanting some pizza. I know, Wine has me wanting wine and pizza. And Wine never sent me any wine. What is up with that, Wine? You said you would send me some from your wineries. That's what California is known for. I thought. Where is the wine, Wine? Haha, right, Dora. I might throw one in the oven right now as we speak. Wine and pizza. Just let me know. Haha, I got you. I'm letting you know right now. Bring it. Send it. All right, guys. I think I'm gonna go to bed. Thank you so much for hanging out. Thank you, thank you, thank you. Please continue to watch and comment on my stuff. Bedtime, okay, no problem, it's on the way. Thank you so much. Good night, everybody. See you tomorrow.